resolution of identity. Yesterday we did. Do you remember it? So that is what I mean. If you take an orthonormal basis and construct such a sum, then that is identity. See, you have to revise what is being taught in this class. Otherwise, you will not. You will be just an outsider. Right? So this is I, and therefore this is equal to psi A psi, which we already know that this is the average value. Average value of an operator A in the state psi. That we already proved. Okay. So let me give the. It's also possible to find out the probability of a particular outcome using trace. So let me do that. So P that I will get lambda I as a result is equal to is equal to mod lambda I psi square. This you already know. This we already derived. Okay. I mean, when I look at your face, there is no familiarity at all. So please try to be familiar with all these things. Okay. So this we have derived. So this is equal to psi lambda I psi. Why? Can you justify this? This is a complex number, some z. I want to find out mod square of some complex number, that is z into z star. So that is this into complex conjugate of this. What is the complex conjugate? Just reverse the order. Okay. So this is what I am doing. So this this I can write as summation over k psi lambda k lambda I psi. Why can I write like this? Why can I write like this? Yes, Amit. हाँ? बीच में क्या है? बीच में क्या? I have inserted something in the बीच. Lambda 1 multiply okay is 1 only. So you are just inserting 1. I am again using resolution of identity. I am again using resolution of identity. So this is, I know that summation over k, this projector is I. So I can always insert I. I mean, identity operator I can insert anywhere. No problem. Okay. So that is equal to summation.
I have a suggestion. On that side of the board, I'll just write the identities that we'll reuse often. On this side.
Yeah, I mean, so
that will help you to remember.
Summation over k, lambda k, lambda k is equal to I, where lambda k is n
Was there any other identity that you would like people to remember? Maybe we can add all.
If it comes, I will write it. So, okay. So this is now the question of rearranging it. It's a summation over k, lambda k, lambda I, psi lambda k. So now this is the trace of this this operator. I'm summing over lambda k. K is the running index. So that means this operator is, and this is the trace of this operator in the in this this thing, in this expression. So this is the trace of lambda I into psi. So if I write lambda I as an operator EI, so I replace this projection operator on the eigenstate, ith eigenstate lambda I EI, and this I'll use as rho. So I'll denote this operator, projection operator, by rho. Then this result I can write it trace of EI into rho. Okay, so let me complete this measurement also. See, because measurement is important and it seems set of measurement operators k equal to 0, 1, whatever. Okay, so if there are n eigenvalues, that is a measure, I mean the dimension is n, then it is n minus 1, 0 to n minus 1. And the property, defining property of these measurement operators is this. Pk, probability that kth result, kth eigenvalue will turn up, is given by, when I make a measurement of A on psi, is given by mk dagger mk psi. Now the probability that some result will come up is 1. That means this probability Pk over k is 1 equal to this. So, but then I use this, so that means summation over k psi mk dagger mk. So, okay, so mk psi, which I can write as psi into bracket summation over k mk dagger mk psi, and this expression I want it to be 1 because this is the same as the total probability. No problem? The probability, I sum over all probabilities over k. Okay. So if these are to be equal, then it means that So measurement operators must satisfy this equation. Okay. Now let us specialize by choosing measurement operators to be projectors. So let me do that. So my MK, I am choosing KK, where K is the orthogonal basis, K runs over the orthogonal basis. Okay, so 0 to say K equal to 0 to n minus 1, where n is the dimension of the space. So the probability of getting the result K, some result K, is, I can find out what is Pk. Pk is psi K dagger, because now my Mk is this. So Mk dagger Mk, so this is Mk dagger and this is Mk. Psi. But we have proved that. What can you do with this projector KK dagger? Do you have any result about it?
P square is equal to P.
Huh?
P square is equal to P.
No. That is right. But we have proved something else. It is something which involves KK dagger, projector dagger. What is it? Tell me. We proved it. Yes, we proved that a projector is a Hermitian operator. That means it's equal to itself. That dagger is equal to itself. So just this. See, if A is an Hermitian operator, then its adjoint must be the same as itself. Okay. So this is the thing. So now I get that is equal to square. Now what can you say about KK square? Huh? What probability here? Idempotency. So this KK square is the same as KK. So this is equal to psi k into k psi. So what is this? This is a complex number, this is a complex number. Is there any relation between them? वाचा नीट बघा त्याच्याकडे एकदम काहीतरी बोलू नका हां 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 दे आर कॉन्जुगेट सो इट इज जस्ट so if I use these projection operators drawn out of the basis states as measurement operators, I get exactly what we have been doing up till now, that this is the projection, I mean the probability is of getting a particular result k is just psi k, scalar product psi k mod square. Huh? Psi k, k what? This is scalar product. No, oh, I'm sorry, I'm very sorry. Yeah, this is, sorry, this is, thank you. Yeah, sorry, thank you. It is a scalar part. That's why you are looking at that term probably astonishing me.
One other question. So that K, this one somebody mentioned is an identity. So this is not an identity. This one, this you asked, what is this? This is not an identity. So why is that not an identity? Why is that different
No,
from that?
I'm not summing over.
But that was your question, right?
Yeah.
What is that? And
No,
somebody mentioned.
no, the questions were like this, that suppose you have this mk, then this is the expression for pk. Now I get product of two operators here. So I mean, it was dagger there. The first question was how to deal with this dagger. The answer is that since this is Hermitian, you just forget about this dagger. Then you get the product of a projection operator. That is, if I call this P, then I am getting P square, I mean capital P. But it's a projector, so it is the same thing as P. So I get here. And that's it, I mean. So I get psi k, k psi.
That is not equals to I.
Huh?
That is not equals to I.
I mean, not summing. If you sum over all the projectors out of it, then you get I. I am not summing it. No. So there is no question of I. So this is the. I mean, is there any problem now until now?
You just put the outer product concept and then I think.
Outer product we have done yesterday. Outer product we have done.
You have not specifically called it outer product.
I have called it outer product. This is the outer product is this. This operator is outer product. We did it. Okay. So now this kind of measurement is called von Neumann measurement. Von Neumann measurement, because this was the first model that was given by John von Neumann about the measurement of on a quantum system. But this is a particular case. I mean, you can have a
Projection-based measurement.
projection based. When the operator, the measurement operators are projectors out of that. Yeah, this is called von Neumann. So, okay. So, where is this? Okay. Now we saw how to construct what is the state space of say two or more particles. So say two particles we did for two particles, and we saw that this is if H1 is the state space for one particle and H2 is the state space for the other particle, then it's a tensor product, and we define what is the tensor product. Okay. Especially, and any particular state out of in this particular state space is a tensor product of corresponding states. So suppose here it is I 0 here and 0 here, for example. So this is the state of the second particle, this is the state of the first particle. Then the combined state is, which I can also write 0 0 by convention. But when I write 0 0, I actually mean this. I may not explicitly write this again and again. Same. Okay. So now, yeah, okay. So the question is, this is also Hilbert space. I mean, the tensor product of two Hilbert spaces is Hilbert space. Now, what is a Hilbert space of finite dimension? Any linear space of finite dimension on which a scalar product is defined is called a Hilbert space. So these are two Hilbert spaces, and this is also space of finite dimension. If the dimension of this H1 is m, then H2 is n, then the dimension of this combined space is m into n. That we have seen yesterday. Okay. m into n. So that is what I am recalling from yesterday's lecture. So if this is a Hilbert space, I have to define a scalar product on this space. So without going into details, I will just make a statement how this scalar product is defined. So suppose you have U1 tensor V1. So of course this is the, I mean the corresponding so if I call this H, then H star, I will not prove this, but H star is given by H1 star tensor H2 star. So therefore my bra, I can write this bra like this. This is a bra in H1, this is a bra in, I mean this is bra in H1 star, this is a bra in H2 star, and this is the product. And so this is, I'll enclose it here, and then I have say U2 tensor V2. This is a ket in H1, so this is in H1, this is in H2, this is in H1 star, this is in H2 star. So this product I can write like this: U1 V1, U2 V2. Okay, by this I just mean this, and this is given by, so this is the bra for the first particle, this is the ket for the first particle. So this is given by U1 V1 scalar product into U2 V2. So the scalar product in H1 and scalar product in H2, this is just the product of the corresponding scalar products in H1 and H2. See, I will repeat it for you. What is the bra? What is this bra? This is in H1 star. What means? That means it is a bra which acts on H1. Okay. This is a bra which is in H2 star. That is, this bra acts on H2. Okay. These are the kets in H1 and H2. So this is an element of H1 tensor H2. This whole thing is an element of H1 tensor H2, and this is an element of H1 star tensor H2 star. Any problem? Do you understand this? Because looking at your face, I mean.
Little bit.
Okay. Okay. So this is the situation, and I want the scalar product of these two elements of, I mean the scalar product of I mean it is a scalar product of U1 V1, I mean this so this is a scalar product of U1 tensor V1 and U2 tensor V2. So this is a scalar product of this. So how do I get the scalar product? I have to find the bra for this and then combine here. So that's what I am doing. Bra for this is this, and this is the ket. So I am doing this scalar product. Any problem? काय प्रॉब्लेम आहे? स्केलर प्रोडक्ट कळलं ना तुम्हाला? का स्केलर प्रोडक्ट नाही कळलेला?
Composite state.
Huh?
Sir has created a composite space.
Yeah,
Because
that's
now
right.
we have two qubits. So we have a composite space. So we have to.
नाही पण
define-
तुम्ही वाचा ना, who stopped you from doing it?
हे समजलं नाही ते लास्ट जे H1 आहे ना
हां
U1 ब्रा आणि गेट सर
नाही काय समजलं? हे
त्याच्या खाली
हे
लास्ट
हे हां. So this is, I have not proved it. This is how it comes out. See, I want to tell you, you should understand this is a valid scalar product in H1 tensor H2. That's what I'm explaining. How do I obtain this scalar product in H1 tensor H2? I take this element of H1 tensor H2. No problem. I take another element in H1 tensor H2. No problem. Now I want to construct the scalar product of these two. Oh, I see. This is the button, is it?
Battery extra.
Okay. Hello? Hello? Okay. So this is the thing that I'll write. U1, V1, U2, V2 is equal to U1, U2, V1, V2. But you must appreciate this. How do I appreciate this result? Although we have not proved it. See, point is, we have already emphasized so many times that when the particles are physically far apart, I must be able to deal with them independently, separately. Okay. Therefore, in that case, even if I so-called, construct a combined space, the scalar product on the combined space must come out to be individual product of individual scalar products, because when they are far apart, I don't have to worry about the second particle at all.
Here you got U1, U2, V1.
Huh?
They got
No, U1, U2.
U1, U2.
Sorry, yeah, and U1, U2 and V1, V2. Yeah, that's right. So U1, U2 is a scalar product on H1 and V1, V2 is a scalar product on. So in this product, U1 and U2 belong to the first particle, V1 and V2 belong to the second particle. Sorry, please, I'm sorry. Okay. And finally, in this one Newman measurement, you have to prove that m dagger m somewhere mk dagger mk summation over k is identity. So sum over k, you have k dagger k. Did I prove this? I think I proved it. I proved it, isn't it? No. See. In this, see, now I am coming back to this one Newman measurement. One Newman measurement, last piece I think is still remaining, maybe. So I will prove it again, it does not matter. So this must be equal to I, na? Because summation over k, mk dagger mk must be equal to I. This is mk. In one Newman measurement, the mk is the projector. And this is equal to I. So this, I get rid of this dagger and more again. I mean, this is a projector, this is a Hermitian operator. Therefore, I am getting rid of this dagger. Okay. K, this projector dagger is the same as the projector. It's a Hermitian operator. Okay. So I get rid of that, and this is square of this, but idempotency gives me this, and this is identity. This is the, this is essentially your resolution of identity. So everything is complete. Okay, so now let me go over to the phase in quantum mechanics. Let me first formally state the Bond's rule, and then we'll see what you mean by the phase. Okay, so I am writing this so many times. So this is equal to, this is the same as alpha 0 0 plus alpha 1 1 plus alpha 2 2 plus alpha n minus 1 n minus 1. This is the sum. This sum is this sum. Now these alpha k are in general complex. These are complex. So I can write these numbers as the polar representation. So I can write it as summation over k mod alpha k e raised to I phi k. Any complex number I can write as mod into e raised to I phi. This is a polar representation. Okay. These are called phases, which are multiplying into this each state, and these have extremely important physical applications and extremely important applications. They are used in a fundamental way in quantum computing. I will tell you how it is used in that context also. But before that, let me just repeat the statement of the Bond's rule. What is the Bond's rule? When you have this set psi, okay, and I measure a particular Hermitian operator or the particular physical quantity on this particular system in this state, then the result is some eigenstate, some L, some eigenstate will result. We have seen it so many times, okay, and the corresponding probability is squared. So this alpha k is actually this. So what is the situation after measurement? This is the state before measurement. On this state, the measurement was made of some operator A, some Hermitian operator A or some physical quantity A, and the result is this. That means now the system is, after the measurement, the system is in this one of the eigenstates of A. That means this previous superposition is lost. You don't have any access to the superposition defining the previous state on which the measurement was made. After the measurement was complete, when the measurement is over, the state of the system is one of the eigenstates of A. Okay, and with this probability, or which I can just say alpha L square. Okay, this total statement is Bond's rule. This was first given by Max Born, and this is called Bond's rule. Okay, now let me come back to these phases. Now suppose in this superposition, this phase is always common for all terms. Suppose this happens, then I can take it out. So, or I can use, so what is now the probability? Probability is mod of e raised to I alpha, I phi alpha square that is e raised to I phi alpha star e raised to I phi alpha, that is right. So this is, you have alpha star alpha, which is just mod alpha square, and so this is the complex conjugate of e raised to I phi is e raised to minus I phi. When you carry out this, I mean this star, so sorry, this star, I erase this star and I make it alpha star. So this is e raised to minus alpha into e raised to e raised to I phi minus I phi into e raised to I phi is just 1, and this is alpha star alpha. Okay. So let me continue. Instead of saying that this is phi k, suppose I multiply each term by e raised to I alpha. What is the effect of that? I phi, some phi or some chi if you want. What is the effect? Effect is, if I multiply the whole superposition out by this common phase, then this common phase will come out like this, and now alpha continues to be complex, so I can take star, and then I get alpha star alpha, and this will give me 1. So again the probability is mod alpha square. It doesn't change anything. It gives me the same probability of all outcomes, nth outcome or whatever. So if I multiply the whole superposition by a same phase, okay, it's unphysical. It is not going to give me anything physical, any physical effect. Such a phase is called overall phase. Okay. But now suppose I have all these terms. There are terms in the superposition where you have different phase factors. Then this psi becomes a function of this. Psi becomes a function of phi 1, phi 2 or whatever, phi n, different phases. So let me give an example, that's better. Now suppose I have this consider this. So it's not an overall phase, only one term is multiplied by e raised to I phi, other term is not multiplied. Okay. So then take, say for example, phi equal to 0. Then what is the resulting state? It is 1 upon square root of 2, 0 plus e raised to 0, that is 1. So 1. Now take phi equal to pi. If I take phi equal to pi, what is the state? It will be e raised to I pi. What is the value of e raised to I pi?
Cos pi plus I sin pi.
Yes. So what is cos pi?
Cos pi is 0.
No. Cos pi is minus 1.
Minus 1.
And sin pi is 0. It's 0. So this is e raised to I pi is 1. Okay. Minus 1. I'm sorry. So square root of 2 get 0 minus get 1. So these are totally different states. These are orthogonal states in fact. Okay. These are the states of the so-called X gate. These are the eigenstates of the so-called X gate or the sigma X operator, Pauli operator. We will come to that. And they are orthogonal. They form a basis for a single qubit, orthonormal basis for a single qubit. So you can see how this phi is so important. Okay. So now let me suppose what I do is I act on this state by the Hadamard gate. Since both, all of you are giving courses in quantum computation, you should know Hadamard gate.
No, they are not all giving courses. It
Oh,
will give.
yeah.
But also, what you erase, maybe we'll write on the right hand side because
Where?
we're going to come back to
We,
it.
what?
The eigenstate
Of X.
operator X are the norm. Yes, let's keep that because that forms another. We will come back to that. Yeah.
They are the eigenstates.
Yeah, maybe you can add that they are the orthogonal states and that they are eigenstates of.
Orthonormal. All states are, this is the normalization constant. So orthonormal. And
Thank you.
so those who are not giving any course on quantum computation, you will learn about Hadamard gate in the next lecture or some lecture. I will be teaching you that. No problem. The result, I mean, when I act by Hadamard gate on this state, the result is cos phi by 2 0 minus I sin phi by 2 0. So the resulting function psi is a function of phi. Okay. And now you can see that, I mean, as I vary phi, I mean, as I vary this value of phi, then I get, what do I get? For phi equal to 0, I get cos 0 is 1, sin 0 is 0. So you will get probability for this term, I mean, the probability that upon measurement this particular term will come up is 1. So, okay, so let me write the probability. What is the probability? Probability is P0 equal to mod of cos phi by 2 square, that is equal to cos squared phi by 2, which I can write as 1/2 into 1 plus cos phi. So P1 is equal to minus I sin phi by 2 mod square, that is just sin square phi by 2, that is equal to 1/2 into 1 minus cos phi. So these are the probabilities. Let me, so if you know, so phi equal to 0 is 1, so this is 1 plus 1, 2 divided by 2 is 1. So P naught, and for cos phi equal to pi by 2, this is 0, so this will be 1/2, and for phi, I mean phi equal to pi, this will be minus 1, so 1 minus 1 is 0. So this is pi by 2, this is pi, so you will get this to be 0, sorry. Then again 3 pi by 2 and like this. This will be a curve as phi versus P0 is this. Phi versus P1 is, okay, phi is 0, this is 1, 1 minus 1 is 0. So your P1 will be 0 for phi equal to 0, and this for pi equal to pi it will be 1. I'm not down, like this. So this is the, you can see that as phi varies, the probabilities, amplitudes vary and probabilities vary. This is the main thing. This is a handle, this is a parameter, and it can be experimentally implemented by a circuit, quantum circuit. So you can, now to give you a familiar picture, let us do it for phi equal to 0. So you have phi equal to 0. I have, as I've seen, P0 is 1, this is 1, and this is 0. P0 is 1 and P1 is 0. So I get the histograms like this. So this is P0, or this is, I will just say Ket 0, and this is Ket 0, and this is Ket 1. So Ket 1 is 0. There is no amplitude here, no probability here. Okay. So this is for phi equal to 0. Phi equal to pi by 2, you will get cos phi by 2 is 0. So that means 1 and 1 here. So that means 1 half and 1 half. So it will be cos equal to phi equal to pi by 2. It will be so again 0 and 1. So here it will be 1 half and again 1 half. You can view it as your dark and white, bright bands in your experiment. Okay. So phi equal to pi, I think. So phi equal to pi, what will be there? This will be 0. P0 will be 0, and P1 will be 1. So that will be. So this will be, suppose this is 0, this is 1. So this is 0, and this is 1. So this phenomenon is actually what you call quantum interference. What we have demonstrated here is just the quantum interference. Okay, and the beauty or the power of quantum interference is it gives you, there is a parameter by which you can vary the amplitudes. You have a superposition. You can, in a controlled way, you can vary the amplitudes of the superposition. Okay, so for example, there is a famous algorithm due to Grover search algorithm, quantum search. So what you start with a huge superposition, and then you apply this, unitary operators which depend on a parameter by which the state, the number that you want to find out, the corresponding state, the amplitude keeps on increasing, and the amplitudes for all the other states in the superposition go to 0. And when this happens, you make a measurement with a very high probability you will get the correct result. By the quantum interference, you can just push up the amplitude of certain term, suppress the amplitudes, and you can just, depending on the algorithm what you want to do, basically it is the traveling through the superposition. You start with some superposition, and then you by your design you keep on traveling through the superposition until you get your target superposition. So another example I can give you is this. So there is a mesh of roads, something like that, and all these kinds of, there is a mesh like this, and what happens is there is only one aperture here and one aperture here, something like this, and there is only one path which joins these two apertures, and I want to find out that path. So what I can do is I can number these paths. Okay, so let me do it. So I will just find that out. Okay, just a moment. No. I just want to write that superposition. I don't want to. Where is it? Okay, I can construct it, but it's after this. So initially, I have no idea. I mean, this all these states are equally probable. All these paths are equally probable. So I'm giving the numbers, say 0, 1, 2, up to whatever paths are there. So some n, whatever. So suppose 1023. There are 1024 paths. If there are 1024 paths, okay. So I give this number. These are the states. And since I don't have any idea before to start with, which is my correct path, okay, that means the probabilities of each of these outcomes is the same. That means it is the same amplitude, and that means it is the amplitude is square root of 1024, 1 upon square root of 1024, that is 1 upon 32. So my state is, okay, so my state is psi, initial state, psi equal to 1 upon 32 summation k running from say 0 to 1023 e raised to I phi k, whatever that may be, k. This is my initial state. Equal probability for all. Okay. Now suppose I have unitary transformations by which I can push the amplitude of the correct state and suppress the amplitudes of the, and that transformation will always depend on, use quantum interference. That let me tell you always. So that if you have such a transformation, then I can say I will have u n minus 1, u n minus 2 up to u0. Suppose, I mean, I'm just imagining that I'm applying these unitary operators here, such that it becomes epsilon. Let me, we'll just see this, upon 23, square root of 123, k equal to 0, k not equal to L. L is the correct path number, 1023. E raised to I phi, e raised to I phi k, plus square root of 1 minus epsilon square L. So epsilon is a small quantity. So what is the probability that any other term will come up? I mean, that is just for each term it will be epsilon upon square root of 1023, epsilon square upon 1023. This is the probability, okay. And since there are 1023 terms, this 1023 will go away. So this total probability is epsilon square, and this probability is 1 minus epsilon square. Square root of will go because I am squaring it. So that is equal to. So the sum of the probabilities is 1. That's what I am justifying it. So the sum of each term, probability of this each term is epsilon square upon 1023. You have any problem? Each term here. This is the amplitude, common amplitude that is coming out. Because amplitude for each term is the same. So this is coming out. So this is epsilon upon square root of 1023 is the amplitude. Each term has that amplitude. So the total probability I have to square this and add for each term. There are 1023 terms. So this will go away. I will get epsilon square, and this will be 1 minus epsilon square. So your total probability is 1. So this is correct. This superposition is correct. But now if I make a measurement on this, now I have got this superposition. I make a measurement on this. What will happen?
Most probably we get
I will get L out. Okay. So this is a very important strategy in constructing quantum algorithms. That's therefore quantum interference is at the root of quantum computing, constructing algorithms for quantum computing.
Why do we call it quantum interference?
Because it is interference coming out of superposition, and superposition is a quantum phenomenon.
Superposition.
Yeah.
Superposition interference.
Yeah. Quantum interference, how did we get it out of this? How did we get this interference out of this? We calculated the probabilities and they are functions of phi, and we got the interference. Periodic functions of phi. We got the interference. How about you? Okay. Fine. Any questions? Any questions? Huh? No questions. So either all of you have understood everything or the other way. Okay. So this is an example that I have given you. So yeah. So that is about quantum interference that I wanted to tell you. So okay.
Can you give the note for this?
This is my book and it is yet to be published. So I cannot distribute it. That is the problem.
But the other bit, so one other thing that we're doing is Professor Zoe has kindly shared the book, the notes.
With the condition that it is not to be shared by to anyone, but that some of the parts are in that active.
That's what I'm trying to say.
Huh.
So the notes have been condensed, the book has been condensed onto LMS. So the LMS is a short form of the book,
Yeah.
and we will do the tutorials of the active learning at the right time.
Okay. So now we'll go to another extremely important concept in quantum computation, namely the entangled quantum states. Let me just think whether I am missing something before, which I wanted to say before, but I don't think, because I think everything is covered. Okay, fine. So let us go to this quantum interference. I mean quantum, not quantum interference, quantum entanglement. So we are doing quantum entanglement. Now suppose you have a, or maybe today let me, instead of starting with entanglement, let me start with formally introducing qubits and the effect of multiple qubits. So that will be better. Okay. So what is a qubit? Qubit is a, stands for a pair. Which pair? A quantum particle plus a such a pair forms a qubit. So you have to choose a quantum particle and you have to choose an observable on that quantum particle which has only two eigenstates and two eigenvalues. The eigens, I mean there are many observables which can satisfy this. You can choose any one of them. There may be many observables which will satisfy this. So, huh? I mean there may be many observables.
Not observables, eigenvalue must be true.
No, eigenvalue is observable. So there are many observables who having only two eigenvalues and two eigenstates. There may be many. You can choose any one of them and make a qubit.
Anyone or
No, no, one. Any one. Yeah, yeah. No, 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 no. There is no range. There are distinct observables. So you have to choose out of the set of such observables. You can choose any one. Okay. No, 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 no. They are not wasted. You can transform from one situation to other situation whenever you want. We will explain that. Okay. So whatever is convenient, you can do that. So that is a qubit. So these eigenstates I call 0 and 1. The eigenstates of this observable are called Ket0 and Ket1. I mean, we denote them by Ket0 and Ket1. Now, how many states, possible states, how many states are possible for a qubit? Answer this. How many states in which qubit can stay? Can be? How many possible states? Infinite. Why?
Alpha superposition.
Any such state is a possible state of a qubit. And since alpha and beta are continuous, they can vary continuously, that means what? That means there are infinite states. In fact, there could be, I mean, they are not even countable, but that's not going to affect us anyway. So a qubit can be prepared or can stay in infinite states. Compare with a bit. How many states a bit can stay? Only two, 0 or 1. So you start appreciating the power now of quantum computing. So let us see this. So suppose, say A1, A2 are the real and imaginary parts of alpha.
So alpha and beta can be negative also.
Huh? Yeah. Alpha, beta, no problem. We are concerned with mod alpha square, mod beta square. If they are negative, it is you have a pi, e raised to I pi phase. That's it. Okay. So A3 and A4. So I am choosing that way. So suppose alpha has these real and imaginary parts and beta has this real and imaginary parts. Then this condition mod alpha square plus mod beta square equal to 1 just becomes, A1 square plus A2 square plus A3 square plus A4 square equal to 1. Equal to 1. You know, mod alpha square is just square of the real part plus square of the imaginary part, like this. Any problem? No problem. So now what I can do is, I just want to find out what are the all possible values of these 4 parameters which will satisfy this equation. The answer is, I can choose any value of A1, A2, A3, A1, A2, A3 such that A1 square plus A2 square plus A3 square is less than or equal to 1. And that way this equation will then immediately fix my A4. That's it. So if I now draw a 3-dimensional space, then choosing this triplet means I choose a point here, and what is the distance of this point from the origin? The distance square is given by A1 square plus A2 square plus A3 square, and this is to be less than or equal to 1. So all points satisfying this condition, these are the points that will fall on a sphere, unit sphere. Okay. So when they are equal to 1, they will fall on actually the sphere, and if they are less than 1, then they will be interior points. Now it turns out that the states which can be superposed, which I will call pure states, are always on the sphere. They are the boundary points, or they are the sphere on the sphere, and all the interior points are represent so-called mixed states, but we have not seen these mixed states. I think I will have to speak about mixed states as well, but that we will do later. So the interior points correspond to mixed states, while the points on the sphere, that unit sphere, correspond to the states which can be superposed. Mixed states cannot be superposed. So that means they are pure states. These are called pure states. So this is the picture. This sphere is called Bloch sphere. In honor of Felix Bloch, who first modeled this in the context of NMR. Felix Bloch called Nobel Prize for his work on NMR. He is extremely more famous about his Bloch theorem in solid state physics, but he got the Nobel Prize for his work in NMR. In that work, in the context of that work, he constructed, and he called it Poincare sphere, but this is the same. Now we call it Bloch sphere. Okay, so now now it turns out, which I will not do that, I think. It turns out that, so every point on this Bloch sphere corresponds to a possible state of the qubit. Okay, that will define A1, A2, A3. That's it. So that will define the A1, A2 will define alpha, A3, A4 will define beta, and that's it. The superposition is defined. So this is every point will correspond to a possible state. Now it turns out that the points which are diametrically opposite, like this, they are orthogonal.
Lying in the same plane.
No, not lying in the same plane. This is a sphere. I'm drawing it on the board. So
Can be on the one plane. There can be
no. Any two diametrically. Take a point on the sphere.
and any other point.
Take any point on the sphere first. Join it to its origin, the origin of the coordinate system, and extend that to get the opposite direction. That we will get that pair. That pair will correspond to orthogonal states, orthonormal states. That means they will form a possible basis, orthonormal basis for a qubit. Okay? We will not bother to prove this, but that's what it is. So now suppose I choose my point on the north pole to be Ket 0, then I extend this down and I get Ket 1 here, because the state orthogonal to Ket 0 is Ket 1. It's a Ket 0, Ket 1 is a eigenbasis of the observable we have chosen. That is an orthonormal basis. So that's what. So similarly, you get, if you have along x-axis, you get these 2 points. Then these 2 points correspond to this these 2 states, which are the eigenstates of X operator, like this. Okay. So you can map any. In fact, you can map any. Okay. So I'm not doing all the algebra, because that will take a lot of time. But I can write this as. Theta, let me call it theta. Okay, so I think this is 5/2. So then you can theta and phi are now the polar. I mean the theta is the polar angle and the phi is the azimuthal angle, and you can just vary this to get the point. I mean, if you are given the state, you know theta and phi, you find out the point which corresponds to it. Like that. Okay. Is it okay? I have not derived this form, but you can derive it. It's no problem. Yeah. Huh?
In usual coordinate system, x-axis and y-axis,
Huh.
in which x-axis and y-axis are basis vectors.
Yeah, because they will give the opposite points.
Then I'm saying in normal coordinate geometry Euclidean,
Huh.
they are 90-degree apart, but here it is 180. Basis vectors are
No, that is because phi by 2, theta by 2, these occurs. That I am not going to those details, but I mean, point is that this is the state, and you have to find out the point on the sphere. Okay. So if that means the point on the sphere will correspond to phi and theta. That is why. I mean, phi by 2, theta by 2 occur in the state, while the phi and theta are the corresponding, you take to be corresponding azimuthal and polar coordinates on the sphere. That's what. That is the reason.
What is theta on sphere and what is phi on sphere?
These are the azimuthal and phi is, do you know the azimuthal angle and polar angle?
Theta, phi, some idea.
Do you know the polar angle and azimuthal angle? So this is, suppose this is your coordinate system, and this is a vector, this is something, a point, then this line making angle with z axis is called theta, that is the polar coordinate. Then you draw a perpendicular and join it here. The angle that this base line makes with the x axis is called phi. This is azimuthal angle, this is the polar angle. So you get this theta, you take theta to be the polar angle, phi to be the azimuthal angle, and you get the point on the sphere. Okay. So this is the block sphere construction. This can be used in many other ways also, but we'll see it later if we come to that. Okay. So this is all about, I mean, whatever we want to learn about the single qubit and its states. Now go over to say 2 qubits. So 2 qubits, basis states are 0, 0. It just means that the first qubit in the state Ket 0, second qubit in the state Ket 0. Then 0, 1, first qubit in the state 0, second qubit in the state Ket 1, 1, 0 and 1, 1. Like this. So these are the basis states and these are all orthogonal. So for example, you take 0, 0, 0, 1. So that is equal to Ket 0, 0. What about this? What is the value of this? Fast. 0. Why? Because they are orthogonal, they are basis states. Ket 0 and Ket 1 are the orthonormal states in an orthonormal basis of that single qubit state. A single qubit state space. So this is 0, so this is equal to 0. So these are orthogonal. Okay. So this forms an orthonormal basis. So I take any state pertaining to 2 qubits, I can expand it in this orthogonal basis. So I can write it as, so I can write this as 0, 1, 2 and 3. Why? Because this is the binary of 0, this is the binary of 1, this is the binary representation of 2 and this is binary of 3. So I can write it like this, k equal to 0 to 3, k into, you can write k. So you have, there is some problem. So what do I do? So I mean lambda k into k, not k into k. Lambda k are the coefficients, amplitudes. So now, if I take a single qubit, the general thing is, say, therefore it can store two numbers, two amplitudes here. A bit can store only one digit. It can be either 0 or 1. It cannot store simultaneously 0 and 1. But here it is storing simultaneously two numbers, two complex numbers. Here 2 qubits are storing 4 complex numbers. So this is number of numbers it is storing is 2 raised to 1. For 2 qubits, then number of numbers that it is storing is 2 raised to 2. 3 qubits, there will be 8 states, 8 basis states, 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. Okay, you can write them out. So maximal possible linear combination or superposition will have 8 numbers, 8 coefficients. So it is storing 8 numbers. So that is 2 raised to 3. Hundred qubits, 2 raised to 100 numbers. The 2 raised to 100 is about 10 raised to 30. Yesterday we saw that a trillion is 10 raised to 12, that is 1 trillion.
At the logical point, we take the tea break.
Okay, what is the time now? I have to continue up to 11:30. Is it 11:30?
It's 11:20.
So for some more 5-10 minutes.
Okay, that's why I said at the logical time.
Yeah, logical. 11:30 we can stop. There is no problem. So 10 raised to 12. So how many trillions this is? 10 raised to 18 trillions. Now I want to make a very important thing. See, now suppose you want to store this information, 10 raised to 30 numbers, in a classical computer, the computer that you are using today. Then I will have to store this number with one number in one location. So what should be the size of RAM? 10 raised to 30. So 10 raised to 30 size RAM computer is not possible, isn't it? But this is done by only, what is the size of memory here for quantum computers? 100.
100.
Just 100. That's all. So you need only 100 qubits to store these many numbers. So this is an exponential advantage. This is the first thing. And second is, as I have already told you, that suppose I have psi and some alpha k, I operate by some unitary operator on psi, that is given by so you get a new superposition, and now the terms in the superposition is like this. So acting on psi is equivalent to acting by the same unitary operator on each term, and this action will process a single number. I mean, it will process that single term. So this is a huge parallel processing, which you cannot imagine. I mean, classically it's not just possible. So you see how I mean, exponential reduction in memory and exponential speed up, parallel processing. Okay, and there are many problems which we call classically intractable problems, which simply cannot, I mean, which the kind of memory and these things, there are the problems that are required for, for example, dealing with the chemistry of suppose you want to find out the the evolution of your enzyme in your body, that contains 800 atoms. And this is, I mean, the kind of 800 atoms means suppose each atom has only one state, I mean only two states, 800 qubits, suppose each atom is a qubit. So it has 800 qubits. So this 2 raised to 800 possible states, basis states corresponding to that. So this is just out. So there are so many such problems which are simply classically intractable. And these are the problems where quantum computing will be used, not anywhere, not the, I mean it will not, quantum computers will not replace present day computers. The present day computers, wherever they are useful, you will continue to use it. But there is a large class of problems where they are simply not useful. There you use quantum computing. Now last statement, but extremely important, please be quite attentive about it. Now the question is, I mean, all these numbers are there in a superposition. I don't have to store those numbers. I have to physically create that state. I must have a physical process by which I put that 100 qubits in that state psi. Okay, I am not storing those numbers because if I am forced to store those numbers, I am gone, finished. I just cannot do it. And how do you compute? You actually use a physical process to change the physical state of these systems. So quantum computing is essentially physical. It's a physical process. It's not a computational process like it's not a computational process or a mathematical process which is just put into some kind of, and that is why you for a classical computer you need some few instructions, that is the basic instruction set, and any algorithm, anything that you want to do, you can just convert it into a sequence of instruction sets, instructions drawn from that set. But this is not possible. Each algorithm is a physical process if you want to implement it. That's why I mean that this is a very important thing that you have to understand. Quantum computing is a physical process, and what you aim to do is to control this physical process, the evolution of bits, quantum qubits, the way you want. And this is a challenge. This is a huge challenge, yes. We'll close that.
So just one question. You made the comment about preparing the state. So you have.
Yeah, every state has a preparation procedure. You can prepare that state, yes.
So you have 100 qubits.
See, for example, I start with 100 qubits, each qubit in the state 0. This is typically any quantum circuit will start. Okay. And then you need a unitary operator acting on the state space of 100 qubits, basically in principle, which will take it to some state which is initial state required by your algorithm. Your algorithm is also a unitary operator which acts on the 100 qubit states, which will produce some final state, and then you have to make a measurement to get that thing out. How to design all this to process the information that you want is the skill. I mean that's why quantum algorithms are not very many. Yeah.
And if you have a problem, for example, something in machine learning, which conventionally requires training data set.
Yeah, that's what. Yeah, that. Yeah.
The machine.
Yeah.
Then what's the equivalent here?
Equivalent here are the gates. The neurons are. I mean, it's a deep learning, so neurons are replaced by proper gates, and the propagation you have to design. So this is. I mean, there. I have a paper. I was discussing that. I want to discuss that paper with the Ahmedabad person. We were saying, his name is Pandey or what? RP Singh. So there, what you can do is you can start with the inputting of entangled state into mm, set of qubits and then process it in training, all these stages can be done. There's no problem.
So all the information will have to go in.
Yeah, yeah. Huh?
If you
Yeah. Unless and until you make a measurement, all information is there. The whole information is getting processed. No problem. So the basic core of your algorithm or your process, quantum computing process, is the processing of superposed state. That's why measurement is to be actually reserved only at the end, because in between, if you make measurement, it will collapse to some state and the whole process might become interrupted and becomes useless. Of course, there are situations where measurements are done there are special things, but done in between, but never in the, the basic principle is that avoid measurement within a circuit. You should do it only at the end.
Thank you.
Okay. Yes.
In case
Glad that you are asking some questions. Okay, fine. Yeah, tell me.
in case of entanglement, what
Entanglement we have not started. We'll do that, and then you ask whatever question you want. Okay, you ask whatever you want. Yes,
what
ask it.
could be the possible distance between the two particles?
No, when you entangle, if you want to entangle two particles, you have to bring them together. But once you put them into an entangled state, as long as you can take them anywhere away, okay, provided you keep them in the same state, provided there is no particle interacting and something happen and state is changed, that's
Does
it.
it possible one particle on one planet and second particle?
Arbitrary distance, because this is the basic difference between entanglement and entanglement is a property of a quantum state. It is a consequence of basic principles of quantum mechanics. So it's a quantum state. As long as you don't change that state, it doesn't matter. Physically, in our real world, our experience until that, when you increase the separation between particles, their interaction reduces. So you take any kind of interaction, Coulomb interaction or whatever interaction you want, that goes as 1 upon r square, gravitational interaction and things like that. So that depends on the square. It depends on the distance or the separation between interacting particles. But for entanglement is not derived from these kinds of physical interactions. That is probably one of the reasons why Einstein was totally, he used to call this as a spooky correlation between particles, something like that. Bhutatki. He used to call this Bhutatki. Is it okay? We close or?
Yes,
Is
let's
it- yes.
have tea. Tea is ready outside.
Yeah.
Thank you. And the next lecture will be yours, sir. So shall we get back in 15 minutes after tea?
Yeah.
So 15 minutes.
Anytime
tea
you
break and
say.
we come back, and it's exactly 11:30 by my watch. 11:30. So 11:45 by my watch.
How to close this? That button is inside somewhere.
I'm sorry.
Huh? काय होत नाही हा दिवा लागलेलाच आहे
Focus
other
नहीं.
focus has gone
Focus
back.
का
We'll have to
problem है.
focus it a bit.
Focus नहीं है तेरा.
Oh, I thought Gary had like a chat. I'll just try take 1 minute turn to focus on the
Focus नहीं है.
व्यवस्थित दिसतं.
थोडा एक गोल्डन लुक आहे याला. थोडा गोल्डन लुक आहे त्याला.
नाही ह्याला गोल्डन लुक नाही.
हो आहे.
अच्छा, तुमच्या ह्याच्यात आहे का? माझ्या घरच्या ह्याच्यात दिसत नव्हतं गोल्डन.
पण असं वाटतं ना.
इथे थोडं आहे
हा.
यांच्या स्क्रीनवर आहे.
हे वर्ड म्हणले आहेत का?
नाही ही पीडीएफ फाईल आहे.
PDF.
वर्डची आणले मी
हा.
पण
नाही वर्ड मध्ये आणले असेल तर आपण फॉन्ट
वर्डची
चेंज
आहे
करू
file.
शकतो.
पण जे इथे ठेवलंय ना हे थोडस जरा चमकतंय ते दिसत नाही आपल्याला.
फोकस नाही होत आहे.
ही इमेज चांगली आहे ना.
हा ही इमेज आहे चांगली. हे बघ हे थोडस क्लिअर दिसतंय.
हे अक्षरांच्या
हा, हा.
भोवती पहा, हे इथे पिवळं आलंय. फोकस नाही.
फॉन्ट बदलून बघा.
इथे फॉन्ट बघून
इथे
वर्ड
जो आहे
आहे
ना तुम्ही त्याला
वर्ड
हायलाइट केलं
वर्ड देऊ का
हा.
याच्यामध्ये?
त्याला हायलाइट केलं
Word
आहे का?
हो.
वर्ड फाईल द्या मग मला. चालेल.
ओके ही पहा.
वर्ड मध्ये वी कॅन जस्ट
हा हा
हायलाइट झाले
आता बरोबर आलो पहा. थांबा.
आलं का?
आता स्पष्ट थोडं मगच पैसे स्पष्ट झाले.
मग थोडं काय
आपण
असं
हे केलं त्याला फुल स्क्रीन केलं का?
प्रेझेंटेशन मोडला केलं होतं ना ते बंद केलं.
हा मग हीच राहू दे.
हे राहून दे.
याला पेज डाऊन करून करता येईल.
बरं आता हे राहू दे का? हे दिसतं
दिसतंय बरोबर.
दिसतं
बरोबर दिसतं ना?
आता क्लिअर दिसतं.
हो हो हो.
राहून दे. गोल्डन बॅकग्राऊंड आहे. दॅट्स ओके.
सुरुवात कुठून आहे बघून घ्या.
ते फक्त तुम्हाला मग हाताने स्क्रोल
आता
स्क्रोल करावं लागेल. ठीक आहे.
अच्छा स्लोली असं. अरे
याने करते ना आयरन.
येणे पण होईल.
इथे ॲरो आहे बघा. इथे
Any पण
पुढे
हा
मागे.
दॅट इज बेटर. कारण एका वेळेला चार स्लाइड मागे जायचं असतं.
चालेल. याचे दोन.
थँक्यू. येतो आहे. Okay, thank you. Again, today also I have chosen presentation in this fashion because
There's a question before your lecture.
ha
Yes, sir.
If two particles are entangled.
ha
If two particles are entangled. If there is a change in one particle, so corresponding change will occur in the second particle, irrespective of distance between them.
yeah.
So does it mean that it will occur faster than the speed of light?
No. You should read discussion of Bell's theorem. Bell's theorem. It all started with Bell's theorem. This cannot happen. Okay. Now he is asking if two particles are entangled and taken far away, will the disturbance measurement of one, whether it will affect the other with speed faster than no measurable information will go faster.
No measurable
Okay, that is the crux. You can read it in the discussion of Bell's theorem also. Okay. As I was saying, again, more than half semester, what we normally teach in more than half semester is going to be contained. So as a result, what I have done is, I've chosen to summarize it on the transference. Okay. And strategy is the following. The topics that I was supposed to cover are the laws of thermodynamics, and then statistical mechanics of ensembles, and then as illustration, harmonic oscillators in classical as well as quantum mechanical setting. So what the strategy I have chosen is, I will start with statistical mechanics, derive laws of thermodynamics in terms of definitions that we introduced. So no separate discussion of thermodynamics actually will be there. And towards the end, I will discuss harmonic oscillator, but that will not take more than a couple of minutes in each case, classical or quantum mechanical. So that is the strategy with which I have planned this now. Now, what is the problem? Problem is that you are going to deal with a bulk system. And bulk system means a huge number of particles constituting the system. Okay. So typically of the order of 10 raised to 22, 23, something like that. Now, even if you knew the potential and laws of motion and so on, surely writing down so many equations is beyond human capabilities, right? Writing equations for 10 raised to 23 particles, let alone write, okay. Solving them is much further. So it's not possible to follow the method of dynamics, even though individual constitutions may follow the laws of dynamics, whether classical or quantum. It's not possible. Humanly not possible. So as a result, we resort to the statistical method. Okay. Now, when you use the statistical method, okay. Now, individual particles, for instance, if there are atoms in the system and so on and so forth, हे वरती जात नव्हतं. इथूनच करून पण मग त्याच्यात खालचं कट होईल, पुढच्या पेजवर डायरेक्ट जाईल, खालची लाईन्स कट होतील. खालच्या लाईन्स कट झाल्या. आता पहिल्याच पानावर जायचं आहे. हां फार नको. हां आता पहिल्या पानावर जाऊ. ओके. नाही तर इथलं खालचं कट होत आहे. हां ओके, माउस इज बेटर. Now there is a change in attitude when we go from individual particles to such bulk matter. The variables that we look at are not going to be individual momenta and energies of the particles, but certain newer concepts which emerge, they are going to be used. For instance, you are familiar all with temperature. This emerges. Okay. Thank you. This emerges when you are dealing with large number of particles. On the other hand, if you are dealing with individual particle, temperature of a single electron doesn't really make sense. Okay, we can sometimes use it for bookkeeping purpose, that is another matter. But it doesn't make sense. So the language that is needed to describe physics on various scales is different. So we introduce different concepts and deal in terms of them. That is the first thing to realize. Okay. Now let us begin with the basic construction that we follow in statistical mechanics. Okay, consider an isolated system with fixed energy. Okay, the energy eigenstates of the system of a large number of particles are very complicated. So the whole system consists of large number of particles, and if you look at the energy eigenstate of that, it is very complicated, and we cannot keep track of it. So this kind of a state is called a microstate, a single microstate. Okay. Even if we consider an ideal system that is isolated, no one can prepare such a system which is completely isolated from the remaining world. There are minor interactions with the outside environment. However good shading you have provided, there will be minor interactions with the environment, and they cause small perturbations in a given system. As a result, what will happen is that the states will keep changing. Okay, states will keep changing, and since the energy is fixed, transitions from any microstate to another microstate will be possible only provided the energies of these two are same or nearly same. Only then there will be transitions. So this is the point to keep in mind. You have been probably made accustomed with the terminology of pure states and mixed states, so that's why that last line is there. Beg pardon?
Transition means here.
Oh, microstates are quantum states. Okay. So from one state, because of the action of perturbations, however small perturbations, you don't remain in the same state. You go to another state. That's what I mean by transition.
Same particle go always.
It's not one particle. It's a big assembly of particles, large number of particles. I'm talking about the state of all those particles together.
One particle go to other state.
Not one particle, one whole bulk. So, for instance, if you have liquid in a beaker, we are talking about the state of the whole liquid. And from one of its state, it goes to another of the state of that liquid, for instance. Or if you have a solid, we are talking of the state of the whole solid.
Where it is useful for us.
You will see now. Okay. That is the whole purpose of the lecture. Okay. So, since the energy is fixed, there is only non-zero probability for states which have energies close to the given energy. Let us denote by n, okay, this n, basis of states of that basis in the space of states of microstates. And the probability that the system is in state n is Pn. Okay. Given system is in that state. So if you, for instance, have an observable O, its expectation value is not just n(O(n). It is multiplied by the probability that it is in the state n, and then you take the sum. So that is the quantity, that is the expectation value. And our goal is really to know what is this Pn. Okay, that is the thing. Now if you consider the system which is left to itself for a long time, then it will ensure that the energy and momentum of the system have been sufficiently redistributed, and any memory of the initial conditions is completely lost. Okay, any memory of the initial condition in which you prepare, in which you have put the system is completely lost. And then the probability distribution will become independent of time. Okay. These expectations, if you consider the microscopic observables, that means observable for the bulk system, they will also be time independent because the state has reached it is more or less independent of time. Such a state is called an equilibrium state. And classical thermodynamics deals only with such states. In fact, in classical thermodynamics, there is no variable with the dimensions of time. Okay? We are going to do statistical mechanics for such states, equilibrium statistical mechanics. There is another very important branch of non-equilibrium statistical mechanics. I will not touch that. Okay. Now, what is the basic assumption? The fundamental assumption of statistical mechanics is for an isolated system in equilibrium, all accessible microstates are equally likely. I will talk about the word accessible in a minute. So all possible microstates, they are equally likely. Now what does one mean by accessible? The word accessible referring to state is that any state that can be reached due to small perturbation felt by the system. So suppose if there is one microstate and a tiny perturbation disturbs it, it will go possibly to another state. Okay. So such states are said to be accessible states.
Does accessible means measured?
No. This means you go from one state to the other. The number of states of the system that are accessible is omega, corresponding to a given energy E. So that omega is a function of E. We will introduce other parameters later. Okay. The primary parameter that we have introduced is energy. And the probability that the system is in microstate n is therefore 1 upon omega E. That is the probability. The probability that the system is in a state with energy E prime which is different from E is 0. So only if the state is in energy E or a very small amount around E, which is denoted by E plus delta E here, in that range where delta E is small enough so that it is small compared to the accuracy of any measuring apparatus, but large compared to the spacing between the levels. So for such microstates, the levels are going to be very, very close because there are a huge number of particles. So this delta E is larger than that, but of course, no measurements will be able to tell you about whether the energy is E or E plus delta E. So that is the point.
Why is probability 1 by omega?
Because all states, according to our fundamental postulate, they are
It should be
equally likely.
omega by total number of states.
No. Total number of states is huge, but that is not what we are talking about. We have fixed the energy.
Omega
So only on that shell our states are found now. So it's not over all possible states. whose energy is very close to E. Only those states are accessible.
Sir, omega E.
That's why.
Favorable conditions, the total number of
Huh?
favorable conditions are omega E. Should be on top of probability.
Where?
The P of n probability the system with energy E.
Yes. So this omega E refers to the number of accessible states. Okay, so this is the number of states. Other states with different energies are there, but they are of no concern to us, because the system can move only in these states. Okay, since the energy is fixed. Therefore, system which is prepared in one of the states can go to one of these other states with the same energy E, or at most lying in the band between E and E plus delta E. That is why this is the probability. Now, the ensemble that we are talking about with this probability distribution is called the microcanonical ensemble. Okay. It's a collection. Basically identical copies. Now, having done that, we immediately define an important variable. The entropy of the system is defined to be K, where K is the Boltzmann constant, times the natural log of omega. Okay. Now you may wonder why log, why not just omega? The number of states is huge. Okay, and another physical reason is that I want entropy to be an extensive quantity or additive quantity. Right. So if you have power laws or exponentials, they won't add. But if you take the logarithms, they will add. So that is the reason. Since I want S to be proportional to the number of particles and have the extensivity, this is the motivation behind introducing the logarithm. Now let us study immediately about entropy of two such systems. Suppose there is a system, system number 1 and system number 2, and their energies are E1 and E2. Okay. These two are non-interacting. They don't affect each other. Okay. Then the total number of states of both the systems is just the product, because you can hold first system in any state. The second will be in omega labeled by E2. Similarly, opposite you can do, hold the system number 2 in one of its states, and the first particle can be in one of its possible states. So as a result, total number of states is going to be the product. Since the total number of states is going to be the product, if you take the logarithm of that product, logarithms will add. As a result, the entropy for the combined system is going to just simply add. So this subscript has come up. This S1 is actually S subscript small 1.
Combined system has to be a closed system.
Yes, yes, indeed. Thanks. In fact, these two systems are also non-interacting. Now, this allows us to formulate the second law of thermodynamics, to which we will come step by step. Okay. Suppose now consider two initially non-interacting systems and bring them together and assume that they can exchange energy. But the energy levels of each individual systems essentially remain unchanged. Now there is a catch here. If you let two systems interact, obviously they are going to affect each other and the energy levels are going to change. What we mean is that the interaction is such, is sufficiently small, so that the energy levels are not affected, only energy can be transferred. That is what is the meaning of this. Okay, they can exchange energy, but individual systems remain, energy levels of individual systems remain unchanged. This can happen if you are dealing with a slow process. Energy of the combined system is of course E1 plus E2 because that was the initial energy. But now after the systems have started interacting and they exchange the energy, energies will change. And the first system, for instance, can be any one of the states En which is less than E total, because the energies are going to be rearranged. Okay, they will, energy from first system can go to second, from second system can go to first, and so on. Total energy is fixed, E1 plus E2, that's it. But individual energies can be different. So now, therefore, we take any En that is possible for the first system, and the energy of the second system is E total minus E1. And E1 takes values En, 1, 2, 3 and so forth. So how much, so how many will be the total number of states? Total number of states now is going to be sum over sets of En, omega 1 labeled by En and omega 2 labeled by the difference between E total and En. Because E2, the energy available for the second system, is this difference. And using this definition of entropy, I have simply rewritten it in this fashion. Okay, instead of omega, I have put exponential of entropy upon K. Okay, so this is simply a rewriting of this. Now we can apply our fundamental postulate to the combined system, and the probability that the combined system will be in one of its states is going to be 1 upon E total, omega labeled by E total. Now the important thing to realize at this stage is that the states of the two original systems are subset of this total number of states. Why? Because anyway they were there. For the first system we had fixed energy E1 and for the second energy was E2. But now after their interaction, after energy exchange is allowed, first system can be in any of the energy states, which is of course less than E total. And second one will have remaining energy. So many more states are available to the first system. Similarly, many more states are available to the second system. As a result, the total number of states is going to be large. Okay. So, since the states of the two systems are a subset of the total number of possible states, the entropy of the combined system is going to be greater because you are simply going to take log. So, when you take the log, this condition that S corresponding to E total is going to be bigger than first entropy corresponding to the original energy and second corresponding to the original energy. So that is guaranteed. So this is the important point. This is what crudely speaking one says when one says that entropy increases. This is what one means. Actually, there is no time-dependent process. Okay, we are looking at the system after all the time evolutions have taken place. But when one says that if you bring two systems together, the entropy increases, this is the meaning, precise meaning of the statement. Now, another important point to realize is the following.
So you told energy remains same.
Energy of what? Energy of the total system.
Total energy.
Correct.
Then here you are saying it is increasing.
No. Entropy.
Entropy increase.
Entropy is different. Energy is energy is fixed. There are three entropies we are talking about. S1 labeled by E1, the initial entropy of system number 1. S2 labeled by E2, the initial entropy for system number 2. Then these systems are brought together, and the combined system has entropy S labeled by E total. So these are three things. And what we are saying is that E total is bigger than the sum of these two. Because for the total system there are many more levels possible. All the initial ones are anyway there. In addition, there are more states.
Someone got En energy total.
Right. It can be in energy En, where En is less than E total. Correct.
But En plus and the second system.
Second is E total minus En, remaining energy.
Same.
Because of energy conservation, total energy is still E total.
Then
Okay.
in S1 you should have En. Now why E1 you
No, that is the original entropy.
don't?
Okay, before the systems were brought together. Initial.
After brought together.
After they were brought together, the bigger system has now energy S labeled by E total.
Initially also E total only.
Initially,
Also E total.
energy total was E total, but systems were not interacting. Okay. And then the entropy was S1 E1 plus S2 E2. And now when they are brought together and energy is exchanged, the entropy has increased. That is what we are saying. Okay. So this is the explanation why entropy has increased. Now notice that entropy scales like N. Entropy is sitting here in the exponential. So that means each term here is of the order of exponential of n times something. N is a huge number, could possibly be 10 raised to 22, 23, something like that. So what is sitting in the exponent is a huge quantity, right? Because it scales like n. And therefore, the expression for E total, omega E total, in the summation, this is the summation that we are talking about. Okay. Here, each of them is having exponential, n somewhere in the exponential. Right? Now, when you consider such a sum, the sum will be dominated by exactly one term or terms neighboring to it. Even if the coefficients differ by a small amount, suppose if the coefficient differed by say 0.001%, still in the exponential that coefficient will simply change by that much, but the number n will still be there. So it will still be exponentially huge. So only one of the terms in this sum is going to therefore contribute. Others will be suppressed exponentially compared with one term. And our job next will be to find that one term. So how do you find that one term? Just simply take the derivative with respect to energy and set the derivative equal to 0. Suppose if the derivative becomes 0 at energy equal to E star, then this is a condition. Okay. This is a condition which tells you which term is going to dominate. Okay. So E star is the energy of the first system. We are talking only about energy of the first system. If the energy is E star so that this relation is valid, then that term is going to dominate and all other terms you can forget, even if there are a large number of terms. Now, therefore, you can usually find an approximation for S labeled by total, that is the total entropy. That is S1 evaluated at E star and S2 evaluated at E total minus E star. Okay. That is the more precise expression rather than the intuitive argument that I talked about earlier. Now, once the systems are brought together and the first system has energy close to E star now, it is very unlikely that any other energy will be attained by that system. So original system had energy 1, that energy is not going to be attained. Only energies close to E star is what the system number 1 will have, and only energy is close to E total minus E star is what system number 2 will be having. This is the reason why we call it that there is irreversibility. Once you are close to that energy, the original energy is not going to be attainable. Now, there is a catch here. One must clearly understand that. The most sacred law we consider second law of thermodynamics, but it is used on probabilistic arguments. Yeah. Beg pardon? Is the value taken by E1. By the first system. See, we are labeling the whole thing in terms of energy of the first system. E1 was the original energy where the initial condition for system 1, energy in the initial state for system 1. System number 1 is there. See, system number 1 is there. Its original energy was E1. System number 2 is there. Its original energy was E2. Now, after these two are brought together, the energy of this system is now E star. No, EN is individual. But after the equilibrium is attained, the most probable energy will be E star. And all other energies will not be attained in the sense that the probability of the system being those states is negligible. Okay. And then system number 2 will be in the having the energy E total minus E star. After the combined system has come to an equilibrium. That is the point. Now remember, if the second law that we have introduced in this fashion is having its root in probabilistic arguments, I could as well go back. Why is it irreversible? Now the answer to this is very different. Yes, you can go back to the original state, but the time scale that will be required is such a huge time scale that it is much bigger than the age of the universe. So it is probabilistically possible that you can go back to the original state. But the whole time scales are huge. So this is why we can talk about the irreversibility. Now the next important thermodynamic quantity after entropy will be temperature, and it is defined by this relation. You take the derivative of entropy with respect to E and declare that to be 1 of temperature. Now we will have to actually check whether that E has properties of temperature, because we have just introduced it. Firstly, it has a right units. Why it has a right units? Look at the definition of S. There is a Boltzmann constant there. Boltzmann constant times this T on this T will give you energy that will cancel with the energy here. Okay, so firstly it has right units. Now there is a consistency check. What is the consistency check? Suppose there are two systems in equilibrium with each other. Okay. And at the same temperature. Now place them in contact. Each system is in equilibrium and at the same T. Initially, they were separate systems. At the same T, now you bring them together. Now what do you expect? Nothing should happen. That is what you should expect. And that condition, nothing should happen, will mean that after the realignment we have seen that this equation was satisfied, because the overwhelming probability corresponded only to energy star. So this state was satisfied. Now look at this equation. dS1 by dE, what does it mean? It means temperature of the first system, 1 upon temperature of the first system. And this will mean then the second term will mean 1 upon temperature of the second system. So 1 upon T1 and 1 upon T2, their difference is 0. In other words, temperatures will be the same. So that if you consider two systems at the same temperature and brought them together, and after bringing together, initially they were in equilibrium, after the bringing together they are in equilibrium, and we expect nothing to happen, and that condition is being fulfilled. So at least one consistency check is there. Another check, of course, will be required.
Equilibrium means
Equilibrium is what we talked earlier, that we leave the system, isolated system, for a long time. Then what will happen is that all the constituents, they will exchange energies and momenta and so on and so forth. So this will keep happening for a long time. After a long time, memory of the initial state, memory of the initial condition will be lost. Right?
Final steady state value.
Yeah.
Final steady state value.
final state of the state.
Steady state value.
Equi-
Then whatever is the final value, that is the
Same energy.
Energy is not changing because we have fixed the energy. Okay. Now, suppose instead of two systems with the same temperature, we bring two systems in equilibrium, already in equilibrium, but with slightly different temperatures, small difference in their temperatures. Then, when you bring them together, they will exchange energies, and either energy will go from system 1 to say system 2 and vice versa, whatever process is required. But the total energy is conserved. As a result, if delta E1 is the energy change in the first system and delta E2 is the energy change in the second system, there will be negative of each other. Okay, if one system has lost energy, the other system would have gained, because E total is fixed. Now again you go through the same logic. If S is the total entropy, find out its derivative, well, increment. It is ds1 by dE into delta E1 plus ds2 by dE into delta E2. But this delta E2 is negative of delta E1, as we have just seen here. As a result, these two will, the expression which is the coefficient of delta E1 is ds1 by dE minus ds2 by dE. But this is 1 upon T1 temperature of the first system, and this is 1 upon temperature of the second system. So as a result, the change in the entropy of the total system is this. Okay. Now from the earlier discussion, we know that if we have brought systems together, delta S is going to be positive. We have seen that entropy increases. So as a result, delta S is positive. That means the left hand side is positive. If the left hand side is positive, and suppose T1 is bigger than T2, in that case 1 upon T1 minus 1 upon T2 will be negative. And therefore, unless delta E1 is negative, you will not have delta S positive. Therefore, if T1 is bigger than T2, we will have delta E1 less than 0. So what does it mean? It means that system at higher temperature gave energy because its energy has reduced. So the energy has gone from system at higher temperature to system at lower temperature. This is alternate form of the second law of thermodynamics. What is the second law of thermodynamics in this form says? Left to itself, if you consider two bodies, spontaneously energy or heat will transfer from the system at higher temperature to a system at lower temperature. That is exactly what has come out of this. So second consistency check is this. There is something more required actually. You may ask why 1 upon T and not why 1 upon T square or 1 upon T cube or something else. Now this cannot be settled just by these logical arguments. For that one has to actually compute what happens to a known system, and once you know what happens to a known system, and if this definition of temperature is correct for the known system, then you can bring that known system in contact with other systems, and the same definition will go through for other systems. They will reach equilibrium. And the simplest system that you can handle is dilute ideal gas. For that, you can check, and we will not spend time on that, is that this is the correct definition and not some other form. Now we will introduce auxiliary quantities. First is the heat capacity. Suppose if you have a system, and suppose if you consider addition or subtraction of energy to it, then the heat capacity is defined by as dE by dt. We will refine this and talk about more heat capacities later. So far I have not introduced any other parameter except energy. But suppose if I have other parameters, then we will talk about various kinds of specific heats. For instance, if you have a fluid system, we can talk about its volume, its pressure, and so on and so forth. Then I can have the heat capacity for constant volume or heat capacity for constant pressure, and so on and so forth. At the moment, S is only function of E. Okay. You could alternately consider E to be function of temperature and then consider S to be dependent on E. Just invert the argument. Okay, instead of considering E to be independent variable, consider S to be independent and vice versa. We could do that. Now we consider here S to be dependent variable and consider ds by dt. You just take the derivative, ds by dE into dE by dt. ds by dE is simply 1 upon T, and dE by dt is the heat capacity that we have introduced. So as a result, this derivative is C upon T. Okay. Now why is this relation interesting? Entropy is difficult to measure in an experiment. On the other hand, heat capacity is something more easy to measure. So suppose if you have measured heat capacity, and if you use this formula above, then change in entropy can be computed by calculating integral of C upon T. So if C has been a measured quantity, then you can integrate this and find the change in entropy. As a result, the entropy can be found, okay, while it is difficult to measure. Now notice that this heat capacity as a function of temperature, because nothing guarantees you that heat capacity is constant. It will depend in general on temperature. And in fact, for various models such as solids and so on, heat capacity does change. For instance, Debye's model or Einstein's model and so on and so forth. You can get a formula for that. But we are not talking about formula. This C is a measured thing, experimentally measured quantity. Okay, you measure that and then use that to define. Yes, you make measurements and decide empirical data. Using that you can calculate the entropy. Because entropy directly measuring is not easy. Now, I was remarking that heat capacity being proportional to n is extensive. So, to construct an intensive quantity out of it, you define what is called a specific heat. Specific heat is just heat capacity divided by the mass, which is proportional to n. So, while C is an extensive quantity here, specific heat is an intensive quantity. That is the difference between these two. Extensive is additive, and intensive, yeah, right. Intensive, if you bring two systems together, intensive quantities are not going to change. Yeah. Now here is another very important observation. If you consider that earlier expression for ds by dE and differentiate it once more, you are differentiating 1 upon t, therefore with respect to E, you can calculate this derivative. There is a negative sign. Since t is in the denominator, we will get 1 upon t square and then multiplied by C, which will give you dt by dE, will give you a C in the denominator. Now this quantity is negative if C is positive, because t square is always positive and there is a net negative sign. Therefore, if C is positive, then t square is positive. Suppose if this happens, then the system is thermodynamically stable, because we had not found out what is the stability condition. For that you have to find a second order derivative, and this second order derivative being negative will mean the system is stable. If second order derivative was positive, it will mean that the system is unstable. So if heat capacity is positive, that will assure us that the system is thermodynamically stable. Okay. Having introduced one derivative, now let us consider more parameters in the system. Earlier we just considered one quantity, namely energy of the system. But now suppose I am dealing with a magnetic system, then I can consider magnetization and magnetic field. There is in fact, in general, pairs of variables, pressure and volume. Okay, volume is extensive, pressure is intensive, and together they will give you, will allow you to define an energy. Similarly, magnetic field and magnetic moment. Or if you consider a stretched wire, then the tension in the wire and its length. Or if you are considering a solid, you could talk about the stress and strain. These are all pairs made up of intensive and extensive variables. Okay. Now let us consider one external parameter, namely volume. So we can be dealing with fluid system and we can talk about the volume of that system. Okay. Now entropy will not depend only on E, it will depend also on the volume available for the fluid. For instance, if you consider gas in a chamber, how big is the chamber will matter for its entropy, because that will decide how many states are available. So it is now going to be function of two variables. Earlier we considered only derivatives of S with respect to E or derivative of E with respect to S, but now we can consider also one more quantity, namely derivative with respect to V. So now this being partial derivative, I have shown outside bracket what is kept constant. Okay, here V is kept constant, and now temperature is again the same definition, except that now V is kept constant. So 1 upon T is ds by E but keeping V constant. Now suppose you consider other derivative, that is with respect to V, keeping E constant, then that gives rise to a quantity. This is exactly like what we are doing here. Okay. So that will define a quantity P, which we define as pressure. Now whether it is actually pressure, that we have to verify. Okay. So whether this definition is a sensible definition or not has to be verified. So what we can do is the following. We can consider a chamber with a movable partition. Consider a chamber with a movable partition. This partition moves. Okay, suppose A is the area of that partition, and suppose if there is a small displacement dx, then this is the change in the volume. Now, for having energy, what I require is force into displacement, right? So, if what is going to be the force? If this P was truly pressure, that is force acting on the area A, then using that I can compute the force and then multiply that by dx to compute the work done. So that can be done. The total volume is fixed, but you can expand the first system and second system is shrunk, because if you go from one system to the other by moving the partition, this is what will happen. Exactly the arguments like the arguments before allow us to get this expression. ds is ds by de plus ds by dv, and you can just put the derivative of s with respect to e to be 1 upon t. So this ds by dv becomes ds by de into de by dv. That gives you this expression. Okay. Now this is now rewritten in a slightly different language. Okay. There is a 1 upon t factor here on the right hand side. You multiply both sides by t, so you will get t ds. Then this term will give you a p dv, and there will be dE. So the same relation has been rewritten in this fashion. dE is t ds minus p dv. Okay. This is known as the first law of thermodynamics. Traditionally, from classical thermodynamics, you get exactly this relation. Okay. The left hand side talks about the change in the energy of the system, whereas the right hand side talks about first term, which we will call heat, and the second term is the work. PdV is the work, that is what we have seen here. Okay, PdV is the work done. How about the sign here, whether it should be plus sign or minus sign, that is the question. And that you can easily check. Okay, if this is one system, and if you put more, if you move the this movable partition to the left, then the pressure here is going to increase. Pressure is going to increase, right? And as a result, energy, more energy will be stored in this. So therefore, this changes will be such that the correct sign of energy change will come if you take minus sign here, and that is exactly what we got from here. So this is the correct sign. We can define various heat capacities. As I told you earlier, we defined only one capacity, but now we have one more parameter. As a result, we can define heat capacity at constant volume and heat capacity at constant pressure by taking the corresponding derivatives. Now let us, after discussing canonical, microcanonical ensemble, from which we got two laws, first law and the second law of thermodynamics, which have the same form as what is discovered empirically. Maybe I will jump ahead and show you about classical thermodynamics a little bit. Can you read this, or is it too small? I will read it. Okay. Kutun. If it is too small for, and I will come back to where we left in a minute.
It is visible here right now.
Okay, good. So classical, let us talk a little bit about classical thermodynamics, then we will come back to statistical mechanics once more. Classical thermodynamics is based on few empirical principles which were discovered experimentally. In fact, the history has it such that second law of thermodynamics was first discovered, after which the first law was discovered. Much later, this happened around 1850. Between 1820 to 1850, the second law got various aspects, various formulations, and it got discovered. Yes, the first, one of the first formulations. Then first law was discovered. Zeroth law was introduced around 1930. And the third law also around the same time. I will not talk about third law. Its origin is purely quantum mechanical, so only after a little bit of quantum mechanics you will see that. Zeroth law, what does it say? If two bodies are such that each in equilibrium with a third body, then they are in equilibrium with each other. So if there are three bodies A, B, C, if A is in equilibrium with C and B is also in equilibrium with C, then A and B will be in equilibrium. This is the transitive property. In fact, it looks like a very naive property, very intuitive property, but it allows you to define temperature, empirical temperature. That is the importance of that zeroth law. First law is just based on the empirical observation that energy is conserved. Second law is based on the observation that heat flows spontaneously from the high temperature to low temperature. Exactly these two laws is what we have formulated. Third law I will forget. And now remember, classical thermodynamics uses only macroscopic concepts. On the other hand, statistical mechanics is based on microscopic concepts that we have just talked about. And I told you about various forces and displacements, and in other words, corresponding extensive and intensive quantities. Some of them are listed here. For instance, if you are dealing with a wire tension and if you are dealing with a film, you can talk about surface tension in the area. If you are dealing with fluid, then pressure and volume. If you are dealing with a magnet, then magnetic field and magnetization. If you are dealing with a dielectric, then electric field and polarization. If you are dealing with a chemical reaction, then chemical potential and the number of particles of a species, and so on. Okay, so this was already known before statistical mechanics roughly got discovered. I mean, as I told you, zeroth law and third law were later inventions afterwards. But now we have seen this with the help of one ensemble. How do you get these laws? Now let us talk about a more tractable method of calculating things. This goes by the name canonical ensemble. Earlier, we dealt with a system with fixed energy. We will now do something else. We will introduce what is called a reservoir. Reservoir means a big system. Okay, that itself is in equilibrium. And then we consider our system of interest. That system of interest is denoted by S, and the bigger system reservoir is denoted by R, and that is in equilibrium with S. The system S, its energy is negligible compared with the reservoir energy. And now this system is brought in contact with the reservoir. So that means you are having a fixed temperature, and then after the equilibrium is reached, the toy system that you are dealing with will be in equilibrium with the reservoir at temperature T. This is the question. Now the question is how the energy levels of S are populated if the temperature is fixed. If it is in contact with a reservoir, it is exchanging energy with the reservoir. So again, we go back to our original thing. If E total is the total energy of the reservoir and the given system, then consider the states N. Now here is something that I will explain later. Suppose the states of the toy system S are N and the corresponding energies are En. We count the number of states. How do you count the number of states? You sum over N. Now remember, this sum is on the states, it's not on the energies. It's not on En. I am summing over states. Omega of the, since we are dealing with only the small system, omega E total minus E, there is a mistake. No, there is no mistake. So E total minus En, and then you can, as before, rewrite it in the form of exponential of the entropy. Now this is the point to note. Sum is over the states and not over the energies. If you had summed over energies, instead of summing over N, this would be multiplied by another omega corresponding to the number of states of the system S. Okay, omega S En, you would have to include that as a factor in order to calculate total. But we are not doing that. We are summing over states. As a result, I don't have to introduce this factor. And of course, we know that E total is very large because the reservoir is large, and all the energies of the toy system, they are going to be much, much smaller than the E total. In view of this, we can Taylor expand this expression. We can Taylor expand this. And if I Taylor expand this in the exponential and keep the two leading terms, this is what I will get. Leading term independent of En. Okay, just look at the exponential. It is SR E total minus En upon K. So this is what is the leading term, and then this is the term proportional to the first order derivative. In the Taylor expansion, I have truncated up to first order derivative. Okay, so first two leading terms in there. Now this is independent of N, so you can bring it outside the sum. As a result, this is brought outside, and the sum is over exponential of the, this quantity En by this ds by dE total has been replaced by 1 upon T. Okay, so sum is over En by Kt. There is a factor, there is a sign missing. Okay, there is a negative sign that is missing. This was the negative sign. No, here there is a negative sign. Yeah, okay. Yeah, here. I was wondering what happened to the negative sign. It's there. See, this negative sign is what I was talking about. Here, this is hiding near the bar. So there is no mistake. This is the negative thing. And here also it is, that negative sign is there. Okay. So difficult to make out whether it is there or not, but it is there. That's why I first thought that I have missed the sign. That's not there. Now look at this quantity. If you consider ask for the probability that the system is in state n, the coefficient is this, and therefore the probability Pn is simply this ratio. When you take this quantity and divide by this total, this exponential factor that is outside will drop out. Okay, that is common to both this term as well as this term, this and this. Okay, that will drop out. And what you will be left is exponential of minus En by kT upon sum of all such terms. This is called the Boltzmann distribution, and the numerator is called the Boltzmann weight. And this formula is called the canonical ensemble distribution. Okay. Now what you can notice is that from the right hand side there is no mention of R except one thing, its temperature. So details of the reservoir have all dropped out. Only its temperature is important. Now we will come to this denominator, and that is an important quantity. This denominator is called the partition function. Okay, this is that denominator. It is denoted by Z. This is traditional notation. It came from the German word Zusammensunde, which means sum. Okay. And so this is the standard practice. This beta denotes 1 by kT, and then partition function is defined as this quantity, exponential of minus En upon kT, or equivalently exponential of minus beta En. Then the probability simply is exponential of minus beta En upon Z, the probability that we talked about, this probability. Okay. And all the physical information that you wish to know about the system can be extracted from one quantity, namely the partition function. So once you have the partition function, all the information you want to extract, you can extract from that one quantity. So the aim is to always calculate the partition function. Which quantities can you extract? For instance, maybe I will talk about this property later. For instance, the expectation value of energy turns out to be minus d by d beta logarithm of Z. Another important quantity that deals with the dispersion, namely expectation value of E minus expectation value of E the whole thing square. It turns out to be dE by deta, its derivative with a negative sign, of course, with respect to beta. And if you look at the definition of CV, it turns out to be kT square CV. I will talk a little bit about this relation. Now look at what is there on the left hand side. Left hand side describes a fluctuation. It talks about dispersion. Okay, the dispersion of E from its average value, of course square of that. And the right hand side talks about the temperature, of course K is Boltzmann constant, and CV. So this relates to rather different quantities. On one hand there is a fluctuation, on the other hand there is a heat capacity. What is the meaning of the heat capacity? It describes the ability of the system to absorb energy. Now relations of this, this kind of thing, this right hand side describes either absorption or a dissipation of energy, and the left hand side denotes the fluctuation. So there is a intimate relation between fluctuations on one hand and the dissipation on the other hand. This is one of the simple examples of a general idea called the fluctuation dissipation relation. There is another important thing that you can realize. Expectation value of delta E upon E goes like 1 upon square root n, that you can see from here. In other words, if you have very large system, the right hand side will become smaller and smaller as n increases. That limit is called the thermodynamic limit, and in that the dispersions become increasingly insignificant and everything is concentrated on the mean. This is exactly the relation between microcanonical and canonical ensemble. When we started with microcanonical, energy was fixed, right? How about entropy? How do you obtain it from the partition function? This is a simple formula. Proof is simple. I will skip that. And now free energy. This is the most important quantity when you deal with partition function, because it is directly related to the partition function. This is also called Helmholtz's free energy. It is minus kT log z. So if you know the partition function, you know the free energy. Now what is free about free energy? Why do you call it a free energy? Of course, energy is not free. It means available energy. Available from what? So if you consider a system, its internal energy is E, and suppose if you keep temperature and volume fixed, then whatever energy is available for you to do work, that is the free energy. So that is the word free about free energy. You may wonder why. Freely available under those conditions, temperature and volume being fixed. Okay. So one should really say it is available energy rather than free energy. That terminology should be there. This I have talked about. Now, couple of simple applications is now what I want to talk about. They are so simple that I will leave them as simple exercise for you to work out. We will consider a harmonic oscillator, whether it is classical or quantum, and talk about the harmonic oscillator in the classical and quantum versions. If you can put lights is fine, because now I will write a little bit on the board. Can you put the lights on the board? I mean, it will be just, I will discuss in say 5 minutes, because these things are simple. Yeah, thanks. So consider first the classical harmonic oscillator, which 2 days ago we discussed in great detail. So the Hamiltonian for the classical harmonic oscillator, function of x and p, I consider only one-dimensional simple harmonic oscillator. So the Hamiltonian is p square upon 2m, p being the linear momentum. There is no other momentum, because it is only one-dimensional system, plus 1/2 of m omega square x square. This is the Hamiltonian for this system. Now, I want to calculate partition function for a system of such oscillators. If they are independent oscillators, they don't interact with each other. If suppose there are 2 oscillators and Z1 and Z2 are their individual partition functions, then for the combined system of non-interacting, their product gives you the Z corresponding to the combined system. So if you want to find out partition function for n harmonic oscillators, it is enough to calculate first for one and then raise it to the power n. Okay, all identical harmonic oscillators, same frequency. Why is this interesting? There is a physical model of solids in which you consider solid to be made up of harmonic oscillators and find out the properties of that using assembly of oscillators. It allows you to do all the calculations, but for some theoretical reasons it is not the right. The reason, maybe I will tell you the reason. Assembly of harmonic oscillators, it is not an ergodic system. Another very important model that we use is ideal gas. Ideal gas is also not ergodic. Two very important models that we use are not ergodic. Nevertheless, they teach us a lot, therefore we still use them. But let us come back to this calculation. Now what is it that you wish to do? You wish to calculate the partition function. How do you calculate the partition function? Simply consider sum. In this case, sum will be replaced by integral, because for each value of p and each value of x, you are at a different point in the phase space. So you will replace it by an integral over dx dp. And then what do? Exponential of minus beta times the energy. So my exponential of minus beta into this energy. So beta into p square upon 2m into exponential of minus 1/2 of omega square x square. And of course, this integral you have to do. This is done by realizing that these are simply Gaussian integrals. Okay, you know what is a Gaussian integral, right? Exponential of minus a into b, let us say x plus b, the whole thing square. Such an integral is called a Gaussian integral. It can be worked out immediately. So you use the standard technique of evaluating this integral. There is a minus sign there. This value turns out to be square root of pi by a. Value of the Gaussian integral like this turns out to be this. Now this gives rise to one Gaussian integral, this gives rise to another Gaussian integral. So you can immediately use formulae like this for the Gaussian integral and integrate. I will straightway write the final result. For purposes of counting, it is a practice not just to write this, but put 1 upon h here, where h is Planck's constant. What is the reason? If you want to go to quantum mechanics, instead of talking about x and p as continuous variables, you will talk about cells of size dx by dp whose area is h. That is the reason. So if you do that, then Z1 simply turns out to be kT upon h cross omega, where h has come from here. So far the calculation, there was no h. Okay, but if you normalize it by writing 1 upon h here to compare with the quantum mechanical version, then Z1 will turn out to be equal to kT upon h cross omega. So this is what happens for the classical oscillator. And of course, you can use this, raise it to the power n, where n is the number of particles, you get the partition function for n particles. Let us talk about quantum mechanics now. In quantum mechanics, calculation is even simpler than what I told you just now. Okay. What are the energy levels? Nth energy level is n plus half h cross omega. These are the energies. So you have to use these energies and calculate the partition function. Suppose if you use these energies and calculate the partition function, you will realize you get a simple geometric series which you have to sum, and which can be summed very easily. So I will write down the formula Z1 and see how easy is it. Exponential of minus h cross omega upon 2 kt into sum over n going from 0 to infinity exponential of minus h cross omega upon kt raised to the power n. This whole thing, this whole thing raised to the power n. And as I told you, this is simply a geometric series. You can immediately write formula for that. So if you write the formula for that, you will get, instead of this sum, you will get 1 upon, this upon 1 minus exponential of minus h cross omega upon 2t. Exponential of minus h cross omega upon 2 kt. So this is what happens in the quantum mechanical case. And factor of 2 I have already taken. There is no need for a factor of 2 here. This is what happens in the quantum mechanical case. Having found Z1, you can immediately raise it to the nth power and get the partition function in this case. Okay, I think I will stop here, and we have taken the route that you start with the statistical ideas and then introduce concepts that will allow you to formulate laws of thermodynamics. This kind of approach is taken in some standard references. For instance, if you look at Rive's book, starts with a statistical description. Other books such as Kardar or Huang and other books, they start with classical thermodynamics and then introduce statistical mechanics. Okay, there are very useful lectures by David Tong, which also take this route, statistical ideas first, then it comes to thermodynamics, okay, classical thermodynamics, and then make a connection between the two. So let me stop here. Thank you. Any questions? Okay, so let's stop. Pen drive काढून घेतो. मग थोड्या वेळात सांगायचं ना, कोणाला शंका काही दिसत नाही. त्यामुळे मग लवकर जायला काय.
ओके सर. प्रमोद सर पण येणार असेल तर दोघं
विचार नाही, ते थांबणार दुपारी उमाकांतचं लेक्चर आहे.
बस तिथे थांबलेली आहे सर्वांनी तिथे बसच्या इथे.
दुपारी जातो. हे राहून द्यायचं.
तुम्ही आता तसं ह्याच्याने येत आहे का? या बस. चला.
नाही इकडनं द्यायचं ना
हात धुवायला चाललंय. कडू लागलाय.
मी माझी दिली मला वाटतं.
pass it. Okay, so I will give you a brief introduction, and then without wasting much time on the introduction, I will skip to the contents on the implementation of quantum computing on real hardware, how it is done and what are the intricacies involved in that, without getting into too many details, of course, because each one requires many classes to introduce you the concepts, because everything, most of it relies upon deep understanding about very advanced not so advanced of a quantum mechanics, but at least up to quantum mechanics 2 level of physics, then interaction of electromagnetic radiation with matter, lot of electronics if you are interested in implementing hardware and so on. And then of course, when it comes to solving real problems, then it becomes a completely different game. Then it comes at the interface of computational physics and computer science and so on. Okay, so excuse me if some of the things are repeating in the initial slides, but I have to go with a certain flow, so I will start with that. Okay, so everything that we hear about these days about quantum technologies, quantum computing, especially quantum computing, is something which is like become so much of a buzzword in many circles, and also without knowing complete details of it, there is a lot of hype going around. So one needs to really understand what exactly. But then of course there are other things within the domain of quantum technologies which are very useful. In fact, they have already been deployed in the field for addressing practical problems and so on. So what is this all business about quantum technologies is? It's basically all in the 20th century we heard about, the physics started developing rapidly after the invention of quantum mechanics. Okay, our understanding, the way we look at things in the physical world, how matter actually works at a microscopic level and what are its implications when you try to look at the properties at a macroscopic level. All these are influenced by what happens at the atomic and subatomic level. Okay, things like some solid turning into an insulator or a conductor or a superconductor. Everything depends upon what happens at the microscopic scale with the atoms and molecules that exist in a particular solid. Now, that is one part, and then there are other things like which led to many different kinds of revolutions in healthcare and in industrial revolution, were things like invention of lasers, invention of magnetic resonance imaging and so on, which are basically, and also invention of semiconductor devices, okay, because that brought about the semiconductor revolution and so on. All these happened because of certain things that were going on at an atomic scale, which were discovered or invented in the first 2 or 3 decades of that century. Now, some of the things that are very counterintuitive to what we see in the classical world were things that were actually, it took a while for people to reconcile with those facts and then use those or try to understand or engineer things such that those properties were utilized, and you made all these revolutionizing devices. Like I gave 3 examples, semiconductors, lasers, and magnetic resonance imaging and all those things. But in this century, what is happening is that we are actually playing with those properties, engineering those properties itself at an atomic level, or at levels where you build systems which act like a super atom and so on, where you are playing with these fundamental properties of quantum mechanics and trying to engineer devices and systems to make, in the hope of making a bigger leap in terms of how we develop and look at develop technologies and utilize them. So you all know about superpositions and entanglement, right? You must have heard. Heard. Were there any classes were taken on those yet? Chalu hai, okay, fine. So superpositions, entanglement, then you have the wave particle duality and tunneling. Okay, these are some of the most important properties at the quantum level, which we are trying to exploit, which we are trying to engineer, which we are trying to use them to make all this, to make very faster computers, to communicate in a secure fashion so that you can detect or stop eavesdropping on the way for secure financial transactions or sending sensitive information, to make sensors that we cannot actually use any of the classical sensors to sense certain properties like magnetic fields, electric fields, gravitational fields of Earth, and so on, which we cannot. Classical sensors like simple temperature sensors or simple magnetic field coils based or Hall effect based sensors, they hit certain limit and beyond which you cannot go. I'll talk about these sensors tomorrow. Then you can think of building clocks which will not lose even a second in the entire life of the universe. Right now, the clocks that are used as reference and which actually steer all the clocks in the on the satellites, which are used for, say, global positioning systems and so on, they lose about a second in 10 to the power 16 seconds. Now, we are thinking, the world is thinking of, or not thinking, just thinking, but they are also building clocks which are going to be better by at least 1,000 times of what we have. So one example of that, the use of that is going to be locating your position with, say, sub-millimeter accuracy if you want. Right now it's a few meters, you can go to sub-millimeter accuracy. That's the kind of thing that we are talking about. And also in communications, you want precise time stamping on the bits that you transfer from one place to the other for some of the applications, especially when you go to secure communications, you need all that. So you need the better clocks. You need navigation devices which don't rely on GPS, for example. These days it's a big problem when you go on the warfield. Your enemy is going to stop the satellite signals because you don't have your own satellites. Or even if you have your own satellites sending signals, your enemy can actually spoof those signals and direct you somewhere else. So you need a device that does not depend on satellite for navigation. So such devices can be built using, just playing around with these using these four principles and implementing them in a real device. So the difference between classical bits, you all know how it works, right? All the digital electronics which powers our processors, which are sitting in the computers, cluster of computers or GPUs, everything there, the information that we process is just some transistors switching on and off, with swinging between different voltage levels, and then you take them as your logical zeros or one, and then you build either sequential or combinational logic and build your processors. Okay, so that's basically some transistor inside switching on and off. But when you talk about a quantum bit, it's not a quantum bit, but it's basically you can think of it as a two-level quantum system. Okay, an electron sitting in an atom, jumping from, excited or de-excited from one level to the other, and so on. Like the light that we see from sodium lamps, it's because electrons are making a transition in sodium atoms from some p state to an s state, and you get the orange light. So that is basically some electron somewhere in an atom making a transition between two quantum states. Now these two quantum states, that particular two-level system is your quantum bit, and there is a reason why it's called so and so on, which I will come to later. So that's an example of a quantum bit. But then you can think of many different systems where you have these quantum mechanical energy levels of a system which can be used as a qubit. You can also think of using 3 levels. You can think of using 4 levels, and you can, then they are called as qubits or qubits and so on. Yeah, so your classical bit only has two states. Either the transistor is off or on. There is nothing in between. Whereas for a quantum bit, when an electron is in some ground state and you excite it, there are a lot of things going on there, okay? So when you continuously keep exciting that electron from the ground to excited state, what happens is that because of photons are continuously getting absorbed, the electron gets excited to the upper level, and then the same photons are going to stimulate that electron to emit a photon, and the electron will come back to the ground state, and this process continues, goes on continuously, and the energy in the atom, the electron, it keeps going from one level to the other, and the energy keeps oscillating between the lower and higher energy levels. Now that is basically what we see as an oscillation in the electronic state, and that's called as a Rabi oscillation. Now the thing is, quantum mechanics says that whenever there is an excitation of an electron from the ground, if you talk about a single quantum system, you excite it from ground to excited state. As soon as you do a measurement, the state, I mean, it's in one of the two states. As soon as you do the measurement, the state collapses to one of the two states. Now, quantum mechanics works on probabilistic laws. So every time you do a measurement, you are not going to see the electron in the excited state. There is some probability of seeing, which means that if I have a single atom or a single ion, like we have in the lab, you excite the electron completely safe to the excited state. You do 1000 measurements, close to 99.99% of the times, you will find that the electron is in the excited state. But if you, for example, if you give something like, you turn on this light for a certain amount of time, like this is the x-axis is basically the amount of time you are leaving the radiation on to excite the electron. Now if I leave that light on for say up to this much time, in this case it's 0.5 microseconds, and you do the measurement 1000 times, most of the times, more than 99.9% of the times, you will see the electron being in the excited state. However, if I leave the light on only for this much time, half of this 0.5 up to this time, you do 1000 measurements, 1000 times you do the experiment, 500 times, close to 500 times you will see that the electron was in the ground state, 500 times you see that the electron is in the excited state. So this is what you get. You do one measurement, you will not get a correct answer. You have to do 1000 measurements. That's what is about quantum mechanics. So that's, now to make things simpler, what you do is that you represent these two states as some state of the electron as either in some ground state which could be 0, state 0, and excited state, state 1. What quantum mechanics says is that you can actually prepare the system's state, you can prepare it as a superposition of ground and excited state. And the way that is written is, it's simplistically like this. It's not an accurate equation, but just to understand, it basically tells that this A's and B's, of course you have to square them and all that, these are complex numbers. It will give you the probability of finding the state of that electron either in 1 or 0. So if I had prepared the electron in a superposition of 0 and 1, equal superposition, then the squares of these A's and B's would be 0.5, which means 50% of the time I will see that the electron was in the excited state, 50% in the ground state. So that is what the representation of the state would be. Now if I so this picture here is actually atoms or ions in this case, which are changing state between the ground and excited state. Okay, so they are string of some 7 or 8 ions, which are, so you do some computation on the string of these ions, and then you do a measurement. Measurement means what is the end result. So you see how many times each of these ions is in the excited or the ground state, dark or bright. That gives you the answer of your computation finally, essentially. So that's a quantum register, a string of bits. Okay. Just again a small introduction, a few introductory slides on why quantum computers. So I use a laptop to solve a problem. It takes certain time. I switch over to some powerful workstation. It solves it at a much lesser time, maybe half the time. I put it on a parallel computer. It might take much. It might solve much quicker. Now, when I say fast, how do I compare what is fast and what is slow? Which computer is fast and which computer is slow? So that is decided by how your time scales, time taken to solve a problem scales as your size of the problem increases. Okay, so there are certain problems where the time that it takes to solve a problem increases as a polynomial function of time, size. It may square or cube or whatever, or some complex polynomial. But there are certain problems where as you increase the size of the problem, the time it takes exponentially increases. So this is what we are talking of. When we say certain problems can be solved slower or faster, means these. Now, some examples are, for example, diagonalizing a matrix or searching some database, searching something from a database which is not structured at all. So these are problems which you can say can be solved fast, because the time that it takes scales as a polynomial function of the size of these problems. Whereas there are certain problems, these problems, it can be simplified as by giving this example of a maze. What you have to do, you have a starting point and ending point, and then there is a complex maze, and you have to find the route to get out of it. This is simple. You can just, by looking at it, you can solve. But you try to start making it bigger, it just becomes exponentially difficult to solve this problem. So that is one example. Other example is this factorizing large numbers into prime factors. Small numbers, you can easily do that. As this number increases, it becomes more and more difficult to find the prime factors. And this difficulty is what is used for in the current encryption systems, where when certain data is encrypted, the keys are distributed in terms of this big number where the factors are only known to the recipients of the, and if somebody else wants to crack it, he has to keep factorizing that large number. And right now, I don't know, it's 1048, how many bits? RSA encryption, the latest standard. 129 decimal digits. Yeah, so that
Product of 2 primes, which is very large.
very large. Yeah, so basically it's impossible on any computer on the planet to solve it in any reasonable amount of time. So basically that's the difficulty which one uses. Of course, there are certain algorithms using quantum systems like Shor's algorithm, which actually was the first algorithm which showed that these problems can be reduced to problems which can of this class. So that is why the entire world is running after quantum computers. That was one of the reasons. Of course, there are many other uses now. So to represent the state, so as I said, this two-level system, it can be represented, you can represent it just for visualization purpose on a sphere. So it's basically you take a sphere and then you have two poles which you can represent in the basis of 0 and 1, and then any point on that sphere will be the state of the quantum system. So if it is on the equator, it's basically an equal superposition of 0 and 1. If it is somewhere in between, then it has certain fraction, but then as I said, these A's and B's are complex numbers. This sphere, this is a sphere, not just a circle, so it can be represented by two angles, the azimuthal and the elevation angles of that vector, and you can basically represent the state anywhere on that sphere, making it like a system which can be represented with infinite number of possibilities. So that's the thing. Now again, if I take a single qubit, it can be in two different states. For simplicity, I have taken, say, an electron spin, which is pointing up or down, simplistically looking at it. You can represent it as a superposition of this 0 and 1 state. Now if you had 2, then you have four possibilities, both pointing up, both pointing down, or either of them pointing up or down. Now these are your basis states, or they are called as vectors in Hilbert space. Now you can construct a superposition of all these, and you can write this. So you have, for 2 you have four states, and you can combine them. Then you have, if you had 3, then you have these 8 possibilities of states, and then you combine them. If you take 300 qubits, then the possibilities are so much that it's just impossible to count. It's more than all the atoms that you put in the world to count, okay? So that's the resource availability once you have the qubits, the amount of information. I think I'll not go through all this. It's basically I think somebody will take all this. I think there are experts. You are all giving talks on this? Okay. So I will skip this. Basically, all I want to say is that since it's a two-level system, the operations that are done on this two-level system, first is you can rotate it on that sphere anywhere. That is one operation that you do when you do quantum computation. That's a single qubit. It's called a single qubit gate. Gate is the word derived from our classical computers. In case of classical gates, you have certain set of inputs, and then there is a Boolean expression between the set of inputs, and you get an output. In case of a quantum bit, you have you basically on a two-level system, in order to rotate that vector anywhere, you can do a matrix operation mathematically if you want to calculate how to do that. There are certain different types of matrices that you apply, and they are all these Pauli matrices. So basically, and then what you do is that you combine all this, like you can build a quantum circuit. So there is a single qubit rotation gate, and there is a 2-qubit gate, which form the universal set of gates for quantum computers. Like in classical computers, you have NAND gates. You put, just by having a NAND gate or combination of many NAND gates, you can create any gate. You can create memories and whatnot, and then you can build your logic circuits. For quantum computation, you need only basically 2 gates, a 2-qubit gate called as a controlled NOT gate, and a single qubit rotation. Once you have them, then say each of these line is a state of the qubit as time progresses, and then these connections which are there between different gates, like there is a connection between this gate and this gate. This is a 2-qubit gate operation. Then there is a connection between 3 qubits. These are 3-qubit gates. 3-qubit gates are nothing but some combination of 2-qubit gates only. And so on. You translate your problem. You start with an initial state of these qubits. Do all these operations as a function of time. And then all the qubits here will finally be in some state which you measure by doing a measurement. and then you get the answer of the combination of all these gates, which are basically translated from a real problem into the quantum gates with through quantum algorithms and so on, and you use the set of qubits for practical problems. So that's all you have to do, and I will also skip all this. As I said, there are single qubit gates basically rotating on a Bloch sphere, rotation of that vector. These can be done by these operators. Operators are mathematical operators, but when you do physically, I'll show you how it is done. Then you have 2 qubit gates, different types. The basic one is controlled NOT gate. It basically says that depending on the state of the first qubit, the second qubit will change. So basically, if you had these 2 qubits, which can be of in any of these possible states, only if the control bit is 1, the second qubit state will change. So if the first is 1, the second one state will flip. If the first is 0, the second one state remains the same. So this is a controlled NOT gate. And then you can represent it with a 4x4 matrix operating on a column vector, which is a state of the 2 qubits and so on. Then you have 3 qubit gates. It's basically a controlled NOT gate, double control NOT gate. So the state of this target qubit will change only when both of them are 1. So this is one type of gate called as a Toffoli gate. Then there are many different types. So depending on the control bit state, the state of the 2 qubits get swapped. Anyway, so that somebody else will do in details. This picture I like a lot because it's on some YouTube video. It basically gives you a complete landscape of this entire domain of quantum computing, starting from what quantum computers are, what is the difference between classical versus quantum computers, what are the and up to different physical realizations. There are things about algorithms, there are different models of quantum computing. There are things like you can do completely gate-based quantum computing. There are things like you can do quantum simulations by just using your quantum systems, a set of qubits, set of quantum bits, or quantum whatever, 2-level or 3-level systems, where you map the real life problem onto them and let the system solve the problem by its own. Because when we try to solve a molecule on a computer, then depending on the number of atoms in a molecule, the problem becomes so complicated that the classical computers will take enormous amount of time, and on the way we do a lot of approximations and all that, and you may or may not get the expected answer out of it, which is very important in, for example, designing drug molecules, for example, in a faster way. There what you do is that you see how a real molecule looks like, 2 real molecules, map them, make a system with the quantum bits, and then engineer the interactions between them, which looks like your molecule, 2 molecules, and then you basically bring them together and let it solve for itself, and it will tell you whether molecule A will bind with molecule B or not, which is very important in drug discovery. You need to know which particular molecule is going to bind to a particular protein. You must have seen these lock and key pictures for this molecule. So those kind of things can be done, but that is a different kind of quantum computing. It comes under the domain of quantum simulations. It's not what you call universal computing. Universal computing is where you solve some mathematical problems, any type of mathematical problem, but here it's different. Okay, so I will give you a brief introduction to all the different platforms that are used. Real systems which are actually used to implement computing. So the first there are certain there is a set of criteria that is required to evaluate whether a particular system can be used as a qubit or not. Initially, I gave you an example of some atom where you have an electron in the ground and the excited state. Not all systems can be used as qubits, although they are quantum mechanical systems. It is not possible to use any possible system for doing computing. So this person DiVincenzo gave a certain set of criteria. Now these are used always to evaluate whether a particular system can be used as a qubit or not. First thing is you should be able to initialize the state of the qubits. Like in your classical computers, when you have a register or a counter or whatever, you have a reset pin there. You press a reset and all the states of the different flip-flops are either in 1 or 0, or if the counter could be all ones or all zeros depending on what you want to do. Same thing you should be able to do here. The second one is a characteristic of a real quantum mechanical system. Any atom, when you excite an electron, for example, it never stays in that excited state forever. It is going to decay back to the lower energy state, and that is something one has to live with, because it's related to very complex things in quantum mechanics where these systems interact with an ever-present energy in the vacuum called as vacuum energy, vacuum fluctuations, vacuum electromagnetic fields and so on. At some point the electron is going to get stimulated by these random photons floating around always, which you cannot get rid of. The electron is going to decay back. Now this time for which it remains in the excited state, you need the qubit state to be in 1 as long as you want, before, if you don't, you don't want that to go to 0 when you don't want it to, right? It has to be in 1, but that never happens in real life. The qubit is going to always decay back because of many things. It is going to interact with these vacuum modes. It's going to, depending upon whether it's an atom, ion, or a superconducting qubit or so on. There are other many things that go on in the real systems where that electron gets back to the ground state, or the quantum state goes back to the ground state. That is what is this. You need long coherence times. Coherence times is related to that. Then you need to be able to implement this universal set of gates. As I said, you should be able to rotate that state vector of that qubit on that sphere anywhere the way you want. Okay, so that ability or capability you should have to do that. You should be able to apply this 2-qubit gate. Then once you do apply all these gates, you should be able to read the state of that qubit. Then just having 1 or 2 is not enough. You need to be able to increase the number of qubits to the extent where you can do some meaningful calculations with it. So that's called scalability. These are all for a single node quantum information processor, which means you have a single CPU kind of thing. Here you have a single QPU. Now if you want to network QPUs, quantum processors, 2 more additional criteria that one needs to come up with, and these are those 2. You should be able to transfer the state of these qubits to another system, another quantum processor, which also has qubits, so that you can connect them. Imagine a scenario where you have a cluster that is built with quantum processors. Just transmitting just by reading the states of the qubit, you lose all the coherence, you just get an output, and then you cannot send that in. You can send, but that is of no use, it's not scaling. You have to send the information about this superpositions and entanglement to the other processor. So you need to be able to convert the information, quantum information, onto something which carries that information to the other processor. And that, no, you do entanglement swapping through a photon. So you should be able to map the quantum information onto something, and that's photon, and send it to the other processor and network them. For that, you need a way to transmit it, and typically it's optical fibers through which you send the photon. Broadly speaking, there are two classes of physical systems which can be used for building, which can be used as qubits. One comes under this class of quantum optic systems, which are basically either, with atoms and light. So the examples being, you create an array of single atoms in vacuum, where the atoms are held in potentials, a two-dimensional or a three-dimensional potential wells, where single individual atoms can be located, can be fixed in vacuum, and then you use them as qubits. You can have ions, where you trap ions with certain electric fields which are changing with time, and then create a string of ions. So here we have an ion trap based quantum computer in the hub on the 5th floor, where we are working with a string of calcium ions. Then you can use things like, you have an atom, so cavity, optical cavity, it's like an optical resonator, where you can trap electromagnetic field inside, and then you put an atom inside. So the atom interacts very strongly with the electromagnetic field that is trapped inside the cavity, which is used for your information mapping from the internal state of the atom onto the photon. And the leaked photons will carry the information of the quantum state of the atom inside. Now this picture here is a real picture of light emitted by individual atoms. You can see the size, this size is about 150, 130 micrometers, this square size. In that you have these atoms which are separated by a few micrometers, and then you can use them as qubits. So these are neutral atom quantum computers. And you can create interaction between these atoms to implement 2 qubit gates. I have those slides towards the end. Yeah, I have those. I'll tell you. The other class is what are called as solid state systems. So one classic standard example is a superconducting qubits based quantum computer. So the IBM quantum computer is a superconducting qubits based quantum computer. So superconducting qubits are basically, it's a loop of metal which has breaks in between of less than 10 nanometers, and there is an oxide or insulating layer between them. And when this loop becomes superconducting, then the supercurrent kind of oscillates in that, and you use the oscillatory motion of the supercurrents as your oscillator, or like an atom which has different levels. It's a quantum oscillator. You can do trapping of electrons in a two-dimensional electron gas. So you make some heterostructure of semiconductor, and then you create a layer where you trap electrons, very thin layer, few micrometers, a few nanometers or so. Then you put fingers of electrodes on top of it, and by changing the electric fields, you can actually localize the electrons, single electrons in certain places, and use them as your qubits. The electron can be made to flip up or down by applying a magnetic field and the radio frequency or a microwave frequency, depending on the energy difference between the two states. Then there are quantum dots. Then now people are thinking of using these nitrogen vacancies in diamonds. So if you take a natural diamond, it's not pure, because there are naturally occurring defects where 2 carbon atoms are missing and one of the carbon atoms is replaced with a nitrogen, and there is a vacancy and there is a nitrogen. And this system acts like an artificial atom with certain energy levels which I will tell you tomorrow when we talk about sensing using such a system for magnetic fields. Okay, superconducting qubits. It's basically an electric quantum pendulum. So this is called as a transmon qubit for some particular region, and here is the qubit. So this is basically a aluminum metal with gap in between, and there is aluminum dioxide or some insulator, which this loop is used as a element in a oscillator. So this is basically the equivalent circuit is this. So the junction, these two junctions are shown with these crosses, and there is a parallel capacitor, the equivalent circuit of that. Now this, when you put it in a, this acts like an oscillator, not a simple oscillator, but a unharmonic oscillator. If it were a harmonic oscillator, all the energy levels of this oscillator are going to be same, which is then useless because you can excite the circuit between any of the two levels if you apply energy difference, if you apply electromagnetic radiation of this energy difference. However, this being a nonlinear oscillator, as you go up in energy, the levels start coming closer and closer. And you can choose any of these two levels to as your two-level quantum system. Now, if you calculate the thermal energy of these oscillator modes, they are much larger than the thermal energy at 10 millikelvin. So these qubits have to be kept at extremely low temperature, and the reason being that this oscillation, the energy difference between these oscillator energy levels is so tiny that if you increase the temperature, all of them will get populated, and it behaves basically like a classical oscillator, and it becomes useless. So you have to go to very low temperatures in the range of few tens of millikelvin, depending upon the kind of qubits that you have. And the energy difference can go in terms of frequency, it goes to a few gigahertz. So you need microwave circuits to excite this oscillator. So that is what is used in superconducting qubits. And the one way to excite it is put this atom, this is called as a super atom now. It's not a single atom, but it's a macroscopic atom. You can put it in a microwave cavity, and then you can actually excite the state of the qubit. You can also read the state of the qubit using the same cavity, same microwave cavity, by looking at the reflected power of the cavity. And then there are different types of variations of this qubit. They all have different names. Then there are spin qubits. So what, as I said earlier, so you make a multi-layered semiconductor structure, and then you have one layer which is very thin, nanometers level, and you basically create a two-dimensional electron gas, and on top of that you have these fingers like electrode structures which can actually trap electrons in each of these regions, and by changing the voltages on these fingers you can bring those electrons closer or you can separate them, and by applying a magnetic field now you can make that electron behave like a two-level system. So either the spin projection is up or down, and then if you apply energy difference equal to the two energy levels, the electron will flip the spin. Now that is what is the way you manipulate the state of that electron in the Bloch sphere. And then there are different versions of this. So the idea is basically you trap single electrons with these electric fields. Now the advantage of this, although there is some progress that is being made with this, a few qubits have been demonstrated, they also have to be working at millikelvin temperatures, and there are problems related to the quality of materials and so on, because these qubits are basically made on top of silicon substrate, and silicon has two isotopes. One of the isotopes has a nuclear spin 0. One of the isotopes, which is rare, has a nuclear spin, has some finite nuclear spin. Now that causes dephasing of these electrons. So the purity of that silicon is very important. And the thing is, once these problems are sorted out, people think that this platform can be used to make a scalable quantum computer where you can have billions of these qubits by using standard CMOS fabrication techniques. Yeah. So this is the layer where you have the electrons which are trapped, the 2D electron gas, and you have the electrodes on top which are microfabricated using electron beam lithography and so on, lithographic processes. And you can, by changing the voltages, you can manipulate the potential wells and the number of electrons you trap and so on, and move them around.
Same as conventional MOS.
Same technology. It's
In conventional MOS, because of that quantum effect, electron moves without any voltages from source to drain.
yeah, so you have to control the barriers and barrier depth such that the tunneling is reduced. You are talking about tunneling, right? So that is engineered by the thickness of that, the 2D electron gas layer, where you create the 2D electron gas. Too many of them. Then there is photonic quantum computing. Frankly speaking, I really don't understand what it does. But the idea is that you use, because the simple reason is that you cannot apply a 2-qubit gate between two photons, because photons don't interact at all. When you have two photons, they don't interact at all. The way things are done are slightly different in a photonic quantum computer, although there is a lot of work going on that will generate entangled photons. But after that, how do you apply 2-qubit gates? That is a challenge. So people are talking about encoding the state of the qubit by sending the photons, single photons through different paths, or encoding the state of the qubits in the polarization degrees of freedom. Or people are also that's called discrete variable quantum computing. Then people are talking about using what is called as continuous variable quantum computing with photons, where you generate specific states of these photons, like Gaussian states or some very complex states called as GKP states, which nobody has created yet properly in the lab. They are supposed to be self-error correcting states. So those are going on. And then people are thinking about using squeezed states of light, and then hybrid between the continuous and discrete variable ones. And what they are doing basically is that they are basically setting up multiple interferometers. So you send a photon in, then you split the photon. This is a beam splitter, then it goes to through another path. This photon goes through this path, and it keeps interfering at multiple places. So in China, they demonstrated some 64 qubits or something on a huge tabletop system with macroscopic components. Now people are thinking of making them on a photonic chip, integrated chip. So you have a gallium nitride material, and then you build waveguides on that. You build electro-optic modulators on that, on the photonic chip, and the chip is just a few millimeters by few millimeters. You send light in from one place, and then you read it out from the other state. So those are the things that are being done. Now, when you look at all these quantum computers, of course, in the in media and everywhere these days, you see three platforms that are going neck to neck. Superconducting qubits have been there for a long time, since IBM started bringing them in the market. Now these neutral atoms and trapped ions are actually overtaking superconducting qubits in terms of the quality. Initially, I talked to you about coherence times, right? So those directly affect how accurately you can apply gates. Now, when I want to flip the state of the qubit, say from the south pole to the north pole on that Bloch sphere, I should be able to do it with 100% accuracy. That's just not possible because of technical noise and all kinds of reasons. It's just not possible to get 100%. But people have gone down, for example, in case of trapped ions, they have gone down to a level of about 10 to the power minus 5. You can calculate the percentage, that accuracy. You can call it inaccuracy. So to that level, people have gone. Now that is much smaller than these these are much better in terms of that when it comes to ions with respect to superconducting qubits. Then the speed of operating the gates and number of qubits. Now these trapped ions have gone from 32 to about 98 qubits. So recently, last December, Quantinuum has launched a quantum computer with ions with 98 qubits and very good gate accuracies, or best gate accuracies. Now the speed of gates, it's relative. It's relative to the coherence times of the qubit. So superconducting qubits coherence times are only few hundreds of microseconds at the best. So your gate times are also very small there, tens of nanoseconds. So within the coherence time, how many gates you can apply, that decides the depth of the circuit. So in case of ions, their coherence times are in seconds. Although the gate speeds are few microseconds, it's still you get a large circuit depth. When I say circuit depth, it's for how long you can operate the gates. I'll give you examples of two of those systems with which we are working here in the lab. One is the trapped ions based platform. So this is a toy model of trapped ions based quantum computer. It's like, these are images of light emitted by 3 ions, individual atoms, which are trapped in certain harmonic potential, and their separation is about 10 micrometers between each. Now these 3 are, you can imagine them as these masses suspended with these springs between 2 blocks. Now if you shake one of these masses, all 3 of them will start shaking, and then there will be some normal modes of oscillations of this system. Same thing happens when you do that to these ions, but you don't shake them physically. You move them by transferring momentum from photons to these ions. Now, first thing is you have to trap these ions. The way it is trapped is using electric fields. Now, these electric fields are generated with a set of 4 electrodes where you apply opposite voltage on the diagonally opposite electrodes. But if you apply DC, you generate a potential which looks like a saddle. Okay, because it's electric field. In free space, you cannot create a minima in 3 dimensions. One minima in all the 3 directions. You create a potential which has minima along one direction, but it has a maxima along the other direction. It's like a saddle. Although the electric field looks like that, you put the charge, it will get repelled from one direction, but get attracted to the other direction. So it cannot remain stable. So this is basic Earnshaw's law in theorem in electromagnetics. But then what you do is that instead, say, assume that if I rotate this saddle slowly with certain speed, as this ball starts rolling down, this other side comes here. It gets pushed inside. So you rotate it if you rotate it too fast, the ball will get thrown away. If you rotate it too slow, the ball will roll down. So there are certain sets of conditions which have to be satisfied to keep that ball stable in the center. So that's what you do by changing the rate at which you flip the field. You have to flip the field with a certain rate, positive, negative on these 4 electrodes, and you basically rotate that, and that is what is this trap doing. So along the radial direction, you generate this dynamically stable potential, but along the axis, you can apply a DC potential, same potential, so that the ions don't move along the axis. But in the radial direction, you apply this radio free RF time varying potential. Then you can fold this geometry into different versions, and you can create this planar structure also. So in these 3 lines here, outer lines 1 potential and the central line 1 potential. So it creates a minima above the surface, and this is the kind of trap that is used by, say, Quantinuum and IonQ, where they have a planar structure to trap these ions on the surface. So one of the earlier version of Quantinuum was this racetrack kind of geometry. So you have this these 3 electrodes which are used where you apply radio frequency, and then these light blue and dark blue electrodes are basically to move the ions wherever you want. You can move this entire string of ions. You can select any of the 2 ions qubits, bring them together and entangle them and separate them. So you get one to many connectivity. So in a quantum computer, you also want not only just nearest neighbor or next nearest neighbor interaction, but you should be able to apply this 2 qubit gate between any of the 2 qubits in your available set of qubits. If you look at this IBM or something, they will give you a circuit of the connectivity between different qubits. There are only certain connections that are possible between the qubits. Not everything is possible. In this case, you get connectivity between any of these ions. Then the other thing is, these traps don't need cryogenic temperatures. The ions, so these ions, they are stable, they are just locked there in their positions, okay? It is not possible unless you reduce the energy of these ions, kinetic energy of these ions, below the Coulomb repulsion energy. If the thermal energy, if they are moving around too fast, then the Coulomb repulsion energy is much lesser than the thermal energy. Their kinetic energy is too much. Initially, when we load the ions, it's basically a cloud of ions. We don't see them like a string. Then what we do is that we use lasers to reduce the thermal energy below the Coulomb energy, and then suddenly the ions, they crystallize. It's called Coulomb crystallization. So basically it's a crystal which is formed because of Coulomb repulsion. And along the axis there is a DC potential which is keeping them together, but they are not sticking to each other obviously, because there is they are repelling from each other because they are all positively charged ions. And we can trap so many ions, and this one is basically this trap structure. So these are those 4 blades. I mean, you are seeing only the front 2, and then these axial electrodes where you apply the DC voltage and you create the string of ions. Now, what is a qubit in this in our ion? It's a calcium 40 isotope which is used, singly charged. 1 electron is ripped apart by using light. You photoionize the ion, and then you reduce the energy of the ions by using light, which is exciting the electron from this ground state to one of these excited states. So we use this P state with a laser which is tuned to the transition but slightly to the red. So what happens when the ions are moving, when they are moving towards the laser light, the frequency that they see is in resonance because of Doppler shift, and they absorb light, and the photons are emitted because the electron is going to go back to the ground state within a few tens of nanoseconds, and the photon that goes away carries the energy. Basically, the thermal energy is taken away by photon giving the kick to the atom, photon transferring the momentum to these ions. And at some point the energy goes below thermal energy and they become a crystal. The qubit, there are other levels, there are many more levels in any atom, but this is just a few of them which are of interest. So we use this particular excitation from this S state to this particular D state. Using 729 nanometer light, you can excite this qubit, this electron, from this ground state to the excited state. The lifetime of this state is about 1 second. Whereas for these states, it's few tens of nanoseconds, because these are all electric dipole transitions. Whereas because the change in angular momentum is 1 unit, it's going from S to P. Whereas this one is going from S to D, the change in angular momentum is about 2 units. So it's an electric quadrupole transition. Now, it's much more difficult for this electron to come back to the ground state once it stays there, because the probability of this quadrupole transition is much lower than the probability of dipole transition. So the lifetime is about a second, whereas this is just few tens of nanosecond. So this is used as a qubit transition. You excite the electron here, it remains there with a lifetime of about 1 second. So you can apply many gates before the electron decays. Then there is another isotope where there is a ground hyperfine structure which can be used as a qubit which operates in microwave regime. So this also has very long lifetime. So this one we are setting up now, the other one is set up. How do you do quantum information processing? The first thing that one needs to do is the single qubit gate. So you have this S to D transition. Now since this ion is in a harmonic oscillator, that harmonic oscillator will also have different energy levels, which means when the ion oscillates in the oscillator, there are different energy levels of that oscillator. And since it's very low temperature ion, which is not interacting with the environment, that oscillator is a quantum oscillator. So these energy levels are very discrete and their separations are few megahertz. Now this transition is at 720 nanometer. So you have the ion sitting inside a harmonic oscillator potential. Now what happens is that this level, instead of being a single level, it becomes a ladder of levels. Because here when the ion is excited, if it's in the ground state of this oscillator, which is the harmonic oscillator ground state of the trap, if you excite this, the ion is not moving, but it is only absorbing the photon because the photon is on resonance. But if you come with a photon whose energy is higher by an amount exactly equal to the energy difference between these harmonic oscillator levels, the ion's internal state, the electron, will go from S to D, but at the same time the ion is also going to gain motional energy and it will go from this ground state to this one excited state. Now imagine if you had two ions there, if I just point light at one ion and do this, not only is that ion going to move, but the second one will also move because they are coupled with that spring or that Coulomb repulsion. This is what you use when you want to apply 2 qubit gates, the control NOT gate or entangling operations. I will show that. For single qubit rotation, you just keep this light on for a long time. It will start, the population starts oscillating. Now if you just keep it on for this long, you will see the population getting excited to completely one state. So that's a pi pulse. If you excite the light for only this much time, it's going to give a pi by 2 pulse, equal superposition of the excited and ground state, and so on. Now typically what we do is that we do some Doppler cooling, we do sideband cooling, because once you cool the ion, it's going to be in one of these higher excited states of the harmonic oscillator. So we need to take away that energy and bring the ion to the ground state. So that is one step. Then you do the coherent manipulation and then you measure. So this is the sequence of operations that you do when you want to do computing. Now when you look at the spectrum, I told you, right? So you have a carrier, which means you are not exciting the ion's motional mode, you are only exciting the electron. But if you come with light which is of higher frequency by exactly the amount equal to the energy level difference between these harmonic oscillator levels, you can excite the axial modes or radial modes, because in this 3D trap, the ion can move horizontally, which lead to axial modes. It can move radially, which will lead to radial modes. So by choosing the frequency of light, you can excite the motional modes very precisely. So this is a single qubit rotation without exciting the motional mode. This is the rotation on the sideband as well as the internal state. So the internal motional state and the internal state of the electron as well as the motional mode, you entangle the motional mode with the internal state of the electron. So you can create states like these. For example, if you had two ions, you can create Bell states. So Bell states are nothing but, so both of them in the superposition of both in the ground state and excited state. Then you have this, one of them in the excited state, one of them in the ground state, and then there is a minus sign between these two. So these are four possible Bell states. They are called, this entangled pairs, or also called as EPR pairs. So this is how you do it. You have two ions in the trap. Now when you have two ions, first of all you put both ions in the motional ground state. So you have the internal state of the electron is in the ground state, both of them. The motional mode is 0. This is motional mode, the second one. This is the internal state of the electron. You point a laser on the first ion. This is your initial state. Then you apply a blue pi/2 pulse, which means you excite this electron to this state. So you create a half superposition of this and this. So what you do is that you create this state. You are pointing on the first ion. You create SS0 plus DS1. So you basically entangle the motional mode with the internal state. Now you have to get rid of this motional mode, okay? Because that you don't want. You want to just entangle the ions, leaving the motional mode. Now what you do is that next step is you apply a carrier pulse on the second ion. So what happens is that you change this S to D, and this one remains there only, the first ion. Now you apply a blue pi pulse, this state goes down, but this one has nowhere to go. So you create SD plus DS, and you are back to your motional mode to 0. So this is how you create the 2-qubit entanglement. And then you can, so these are the sequence of pulses. This is the initial state. You apply this pulse, blue carrier with a pi/2 pulse with a phase of minus pi/2. Then you apply a carrier pulse on ion number 2, a pi pulse. Then you apply a blue pulse, blue pi pulse on ion number 2, and you get this state. And then by changing the sign of this pulses, you can change the sign, you can change, by applying an additional pulse, you can basically make these states and so on. So you create 2-qubit entangled states, or the Bell pairs. So this is how, okay, this is some earlier version of the trap that we had in the lab. It's not showing properly here on the screen. So the trap is sitting inside this chamber, and there is a big microscope objective which collects light, because they are very, the amount of light that is emitted by single atoms is very small. And also you have to resolve their positions, they are very close. It's done by using a electron multiplying CCD camera and a very large aperture, numerical aperture objective lens. Earlier we used a Nikon lens. And this is the entire table where you have the control system. There are lasers sitting in one rack and many optics. The trap is sitting inside that vacuum chamber, and these are the pictures of these ions. So by this year end, we would like to have a 20-qubit one working. So that is what we would like to do, and then we would like to move on to going to about 1,000 qubits in next 3 to 4 years. We'll see what happens. These are the different parameters that we would like to achieve. fabrication of the surface traps. These have to be done in a fab. We don't have access to, I mean, there are no fabs in India which can do this. Quantinium is able to do because they are a spin-off of Honeywell. Honeywell has a very big fab facility which makes MEMS-based sensors and all from healthcare to aviation industry. So they have very good big fab. Funding will come. Funding will come. I mean, funding will be a bottleneck, but getting access to fabs is a problem. Because, yeah. So these are some of the commercial ones. So this is a computer, a 3D trap-based computer by Alpine Quantum Technology, where I had worked 20 years ago. Not that company, but the research group. Yeah. Then here, no postdoc. So that was about ions. But now there is another platform which is coming up, which is showing huge promise for scaling up, are these neutral atoms. In ions, we had this Coulomb repulsion, right, which was used for generating 2-qubit entanglement. With neutral atoms, it's very difficult because if you bring two neutral atoms close to each other, the only interaction that exists is a magnetic dipole interaction, which is very small. Now, this is a picture initially I had showed you. This is fluorescence from a series of trapped, many trapped atoms. Now, these atoms are trapped not with electric fields like in the ion trap, but by using what are called as optical tweezers. So, you use an array of focused beams of light. You create a sharp focus of light, and at each of this point, you trap a single atom. Because of AC Stark shift, when you put an atom in light, you must have heard about optical tweezers, right, which hold small biological objects or spheres for doing biological research. Similarly, atoms, when you put in a focused beam of light, the intensity of light at the focus changes like a Gaussian. Now, when you put an atom there, wherever the intensity is high, the light is not resonant with any transitions. It's very far away from transition. There is an AC Stark shift because of the oscillating electric field of light, and you create a potential. Now, if you choosing the right frequency of the light, whether it's above the resonance or below resonance, you can create a trapping well or a hill. So, you typically create a potential well by choosing light which is far red detuned from a transition, and then you can trap each of these atoms in those focus. So, you create an array of focus of light, for a different focus of different light beams, and you trap them. Now, as I said, they don't interact much, but there is a way to make them interact, and that is called as by exciting the electron of an atom to very high n levels. So, when you excite the electrons to say n equal to 50 to 100, what happens is that the separation of the electron from the nucleus becomes very large, thereby creating a very large electric dipole moment. Now, if you have two atoms which are close to each other, whose electrons are excited to these very high n levels, these dipoles repel each other. There is a strong repulsion between the two. So, when the two atoms are close by, you can excite only one of them to one of the atoms electron to high n levels. So, this atom, when you excite to very high n levels, is called as a Rydberg atom, and the interaction is called as a Rydberg interaction. So, that is what you use. So, this is what is shown here. So, energy of two atoms. Now, if you have atoms separated by about 10 micrometers, you can, if you excite one of them to the excited states, the Rydberg levels, the energy increases by some amount. But if you try to excite both of them, the energy is very high. In fact, it's not possible. It's very difficult to excite. Now, when you do that, okay, the electron is very far away from the nuclei. the interactions become very strong. Like you have a dipole-dipole interaction, you have van der Waals interaction. Now, if you don't have any external fields, the interaction goes as n to the power 11. If you take n equal to, if you put n equal to 50, that's very large. So, this is how the energy increases. If you bring two atoms which are in, both are in excited state, if you try to bring them close, the energy increases very rapidly. So, when they are close, only one of the atoms can be excited to the Rydberg state. Now, this is just a comparison of the energy when you bring two atoms together close to each other, when the interaction is of different types. For our ions, it's like this. So, as you bring them close, the interaction is about, in the units of frequency, it's about 10 to the power 11 hertz or so. And it falls very slowly as the distance increases. But if you had, for example, just atoms in the ground state, you have magnetic dipole-dipole interaction, which is very tiny. This is 0.1 here, whereas this is 10 to the power 11. The van der Waals interaction is even smaller. So you basically don't get anything, no interaction between the atoms when they are in the ground state. You have to excite them to the Rydberg state to get any interaction. And the way that is done is, if, like for example, there is something called as a controlled phase gate. So if the state of one of the qubits in the is in 1, only then you should be able to change the phase of the second qubit. The way it is done is here. So you have a control bit, a target bit. These are the Rydberg levels. Now, if the control bit is in the ground state, when you do a 2 pi rotation on the Bloch sphere of this state, you go up and come down, it picks up a phase of pi. Because whenever you do a rotation on the Bloch sphere of that vector, you make a circle or you make a small circle or a great circle on the sphere, you pick up a phase which is half of the solid angle that you rotate on that, right? Yeah. So this is what you do when you rotate it on the Bloch sphere. You get a pick up a phase. Now, however, if I bring this, if I excite this electron to the Rydberg state, if this were here, for example, and I apply this pulse, it goes to Rydberg state, but the energy of the neighboring atom shifts drastically because the other qubit state is in Rydberg state because of the dipole-dipole interaction. When I do this rotation, nothing happens. You don't pick up a phase. So this is a controlled phase gate. That is how you apply gates between the neighboring atoms. So you selectively, what you do is that you point a laser on any of these atoms. Like here, if you point on these atoms which are in blue color, then these red atoms, when you do this phase gate, they pick up a phase. If they are not, then they don't pick up a phase. Now, this system is useful for both types of computing, the gate-based computing and the quantum simulations. In quantum simulations, what you do is that here you create these interactions such that, for example, I create this hexagon without this center atom. You can actually make it look like a benzene molecule, for example, because it has certain, these interactions you can engineer. Then you can create another molecule here of some other shape by pointing the lasers and creating those interactions in a certain fashion, and you can do this quantum chemistry simulations, for example. You don't have to worry about writing wave functions, doing approximations and all that. It automatically solves by itself in no time and gives you the answer. So this is very useful, this platform for that. And in a real system, this is from the Harvard group, you have so in vacuum system, in a glass cell, I mean, we are also setting up this, we have trapped up to 3 atoms, neutral atoms. So what you do is that you create a very spatial, you have a device called as a spatial light modulator, which creates a array of those optical tweezers where you trap these single atoms. Then you have acousto-optic deflectors which focus the light onto any of these atoms and you can move them around. So you have a storage zone, you move these ions somewhere else, do the entangling operations, move them away, and then read out the state. So this is how it is done. Yeah. So you can apply, I just gave an example of a control phase gate. Then you can apply one or two more operations on the 2 qubit and create a control NOT gate between the two. That is just for the first step. Just to demonstrate how the interaction helps in creating a. Yeah, so this is an array of these optical tweezers which are holding the atoms. You can, sorry. You can focus light on any of these and you can apply, you can do the single qubit rotation and so on. And that's it. Any questions? No.
So when it comes to quantum computing, applying the concept of quantum to quantum computing, what are the basic things from quantum physics that are supposed to be clearly understood by a computer software person?
Computer software.
Computer engineer.
Okay. When you are talking about computer engineer.
We want to design algorithms
Ah,
to have
okay.
some type of computations for
Okay, I'm trying to understand your question. Okay. So, translating a real life problem into a set of quantum circuit, there are various steps. First of all, you need to understand how that problem can be mapped onto an algorithm which uses the principles of quantum mechanics. And then once you draw that algorithm, then you translate it into, break it down to the basic gate operations. And then give a set of gates in a time series and give it to us, and then we will implement that. The other part is not my expertise or anything. I don't understand that.
from two different domains will be
Yeah, multidisciplinary, not two domains, multidisciplinary.
Is it possible to make a generalized programmer, logical programmer processor, or it is specific to problem?
So the circuit will be very specific to a particular problem. As long as you can give a quantum circuit which is going to solve your real life problem, you can execute. Now, one has to keep in mind what is the circuit depth my hardware is going to allow me to do, what are the error rates, how many qubits I have access to, total number of qubits and how many qubits I can connect to each other. The limitations of the hardware has to be kept in mind when you design the quantum circuit.
Right now, it's not possible to make it generalized.
Well, right now we still are in a regime where we are restricted to only 100 or so qubits, few hundred qubits. So people are trying to see how that can be used to demonstrate quantum advantage. Quantum supremacy word is gone, quantum advantage, yeah. Yeah.
In this simulation, you are qubitizing macromolecule or some such kind of thing. You qubitize. I mean, actually the object that you use to simulate is the collection of qubits. Each is a two-state system. But here, in the actual macromolecule, it could be something.
Yeah, so it may not be possible for every molecule or anything. One of the things that they did was with these interactions, not of molecules, but they tried to solve this traveling salesman problem on Manhattan Island. Huh.
Simulate a particular physical process, quantum process. That quantum process may not be exactly, may not be able to exactly describe in terms of number of qubits.
Not number of qubits. So you may need more than one qubit or a few qubits for a particular interaction. You can also say simulate certain Hamiltonians. Certain type of Hamiltonians you can simulate using this. You can engineer the interactions between the nearest or next nearest neighbor or something.
So the terms in the Hamiltonian could involve more than degrees of freedom.
Yeah.
That is, so you have to approximate actually. Right?
No, some of them can be exactly mapped. Some of them can be exactly mapped. Yeah.
Some simulator to execute over some algorithm, correct? But simulator is not exactly the actual quantum, correct? Actual quantum computer. Simulator, artificial simulator, like online simulators they use to execute our algorithm.
On a real quantum hardware or classical computer used as a simulator?
As well as some cloud access.
See, it is just you are basically, so they have limitations. You can probably, I don't know, the best one probably goes to 35 or 40 qubits. I don't remember the number. You can, basically what you are doing is you are doing this matrix mechanics on those number of qubits. You are just multiplying all your operators, quantum operators, you are on this multi-qubit system and you are solving. That's it.
So we design algorithm and we want to test whether algorithm giving correct output.
That can be done on a classical simulator for a few qubits. You don't need a quantum hardware.
If it run for 35 qubits, then we can assume it is run for.
No, that I don't know. I mean, the existing ones run can handle up to that. Probably it's 50 now. I don't know. Already the Hilbert space becomes so big that the amount of memory that is needed is humongous. Yeah. So.
IBM is also providing some real quantum.
Huh. I don't remember.
You get some answer out of it. He wants to check whether that answer is correct or not. That you can do classically.
That's what he's saying. So he's saying in a classical computer.
No, basic is your quantum computer. You run that computer, you get some kind of output of the computer. You want to validate that output.
Is that what you are asking?
Quantum algorithm is correctly designed or
no, the output is correct or not. That's
So you are,
classically.
yeah, for up to that many qubits you can do. You can use classical computer and get an answer and you can compare.
if it works for 10 qubits, I can assume can it work for 100 qubits.
Okay, that I don't know. That I don't know. Whether it will scale.
Factorization work for 4 bits. Same algorithm work for 4000 bits.
Huh. Yeah, factorize. I mean, it's that basically there are two things, right, in that quantum Fourier transform and some. That is one thing, and the second thing is period. Phase estimation. Yeah, there are only two things in that.
You can get a circuit to that scale. Algorithm will work.
Yeah, that scale will not get, small scale will get. So small scale.
Same algorithm will work. But whether you can implement it,
Whether the hardware can handle that. Okay. Thank you all for your attention. Huh? Yeah. It's here.
देयर बी रिकॉर्डिंग उसके लिए थोड़ा अच्छा वॉल्यूम चाहिए.
Okay, great.
Yeah, hello everybody. So we have our second industrial visitor for this week, Sujoy from Confluence. Yeah. Sujoy, up to you. You can take over.
Okay. Hello. So I'm here representing a company called Confluence. I don't know if any of you have heard of us, but we are a photonic quantum computing company. And what we are doing is we are building the hardware machine. So we are building the computer itself. So with me also is my colleague Aditi. Aditi is here. So she looks after all the university relations, etc. So you might want to connect with her after this. So what do we do at Confluence? In one line, we are building a universal photonic quantum computer which will leapfrog existing machines. Universal computer, I'm sure this is what you have been talking about for a long time. So a universal computer is one which can run any quantum algorithm. So something which you can run on the IBM machine can also be run on this machine and so on. So that's what universal means. Photonic is what we use, the method for running it. So Umakant was here 2 minutes ago. They do something called ion trap. IBM, Google, that chandelier which you see is superconducting. What we do is photonic. So what we do is we use light. So I'll go into some details of what we do and how we use light. And the reason why people are doing all of these methods is because today's quantum computers are not very scalable. You don't get enough qubits to perform algorithms. Some of you might be trying to run algorithms on these machines. They don't do very well because it's noisy, it's not enough qubits. So you need a machine which is very large, which has maybe 1 million qubits or so. And that's why these other approaches exist, and we believe that photonics is the way to get to those million qubits that we are talking of. Little bit about us. We are a 5-year-old company. We are funded. We have grants from the government, and right now we have about 22 people, mostly in Bangalore. There's 3-4 of us here, but most of the people are in Bangalore. We filed 9 patents. A few more are in the pipeline. I'm going to skip what quantum computers do, because I believe there's been a lot of discussion about that in the last few days. But basically, the idea is that it's a different paradigm of computing. It'll exist with existing computing and do things which cannot be done in existing machines. So why we believe in photonics? The first one I already talked about. It's not. Font is not clear. Yeah, it's very nice on this. So इस पे तो बहुत अच्छे से है. It is a PDF. I can zoom in, but that will not correct these things. One thing you can do is try to reset it and see what happens. No, it's just as bad. ये वाला है ना, मैं अपना कंप्यूटर लगाता हूँ.
हाँ, ये भी चलेगा.
Yes, give me a second. I'll get my computer. Let's just change the computer. इसको है ना
है
it did detect something, but they don't work, no? I think there's a lot of people from engineering colleges here. They can help us out.
Is there a setting on here on Apple
No,
screen?
it should happen on its own.
अच्छा जो आपने झूम किया था ना वो मॉर्निंग में सेम प्रॉब्लम आ रहा था वही लैपटॉप पे अगर लगाओगे तो हो जाएगा ऐसे कुछ सुबह ऐसे ही हो रहा
आ गया चलो.
आ गया ओके
But the general इसका quality ऐसा है.
So, it's a projector problem.
Yeah. So we are not going to get much better. Maybe you want to connect your machine only. This is just hanging now. Let me try it once. चल गया तो अच्छा है.
Okay, let's do it on this.
Just give it like 10 seconds, and if it doesn't work, we'll do it on that. There you go. Something is coming up. Okay. Is this better? All right. So we were somewhere here. So photonics. The reason why we believe in photonics is because the world telecom backplane works on photonic. It all works on 1550 nanometers. So the entire infra is there. And a lot of the other people are saying that eventually we will connect multiple computers together, and that's how we'll increase the qubit count. But what happens here is that unlike normal machines, you can't do a measure and transfer. Anytime you measure something, you lose the quantum state. So you have to connect computers using qubits. So you have to connect them using qubits which can move around. So what are the qubits which can move around? They are photonic. So that's why we believe in photonic qubits, that you're going to need them anyways. And if you're going to need them anyways and you have them, then why not use it for compute, right? So that's what our reason is to select photonic. And photonic quantum computing is done by a methodology called measurement based quantum computing. Here what happens is that photons don't like to interact with anything, including themselves, including each other. So making photons interact with each other is a complicated problem. And that's the reason why people did not know how to do computing. They did not know how to do transformations on photons until they came up with, there's a groundbreaking paper called measurement-based quantum computing, which says that anytime you measure a quantum bit, there is a transformation applied on an entangled bit with it. So if you have two entangled quantum bits, measuring one applies a transformation in the other. And people figured out that this can be used for doing quantum computing because you can do gate manipulation and so on. So we use a form of, when you talk about photons, the earliest ideas of quantum computing were from photons, right? You take the smallest particle of light or wave of light, however you call it, the smallest energy of light, quanta of light is called a photon. And a photon is a quantum particle by default. So you can do computing, you can do everything using a photon is what the idea was. So in computing you need to get two states. So with a single photon those two states are fairly easy to understand. It can either be polarization or it can be, you put it in a beam splitter, which beam splitter did it go into. So this is how simple photonic gates were made, right? But there are issues with this approach. The issue is that single photons are very hard to detect. So detecting single photons with any amount of reliability needs cryogenic temperatures. Also, single photons are very easy to lose. If there is any loss in the system, then you have lost your qubit. So we use an approach which is called a CV paradigm. So that's continuous variable. And it's called continuous variable because we do not use single photons. What we do is we use a bunch of photons, and anytime there is a photon or a bunch of photons, there's an associated electric field. So we do modifications to that electric field, and that is what the qubit is. So the qubit is actually not a photon, but it's the electric field associated with some photons. Right? Sounds complicated, but it isn't. And once you go to that state, then all the photon operations, etc., all the gate operations, etc., become easy to do. So that's why we do it. The complicated part here is how do you generate such a state, right? And that is our patented system. This is something which no one in the world does other than us, this particular method of generating a photon. It's called a cat breeding system. You can go to Confluence online on our YouTube channel or whatever, and we put out a video on how this whole system works. So you can look at the video. You can come back to us if you have any questions, comments, etc. Right? So we believe that our approach has several advantages over existing players. I'm not going to go into details of that. What I'm going to do is also talk about what else we do, right? So this machine which I talked about, this quantum computer, there's a lot of grounds up research going on. We've been working on it for 4 years now. We will continue to work on it for another 3 years before we get a machine which actually has qubits and which you can use in your labs and so on, right? So that's still a long journey. But at the same time, while we were doing this, we've managed to build several other things in the company, which are all again quantum related. One of the first things here is what is called an Ising machine. So one of the applications of quantum computers, the most widely used quantum computing application today is optimization. So you would have heard of optimization applications using D-Wave, etc. Right? Interestingly, optimization does not need a full-fledged quantum computer. You can do an annealing-based optimizer. Right? So this is the Confluence machine. It's an annealing-based optimizer. It's available on the cloud. It's available to buy offline. You will actually start seeing a lot of papers coming out of educational institutions, the IITs, even some companies who are using this machine now to solve optimization problems and showing results better than what classical hardware can do or what even D-Wave can do, right? one of these machines we just sold to IIT Indore, and they have shown that the performance of this machine is better than most systems that they have used so far. So this is a fairly interesting field, and this is very engineering related. So this is something which engineering students can use today and start solving for these optimization problems which happen to exist everywhere.
We need to write programs in which.
So we give a Python SDK for this thing. So if you use Python, you can directly install our libraries and use them. Otherwise, there's an API. So you can call the API from a programming language of your choice. The API comes with its documentation. So it's fairly simple. You need to create a GIG matrix, something called a Cubo, and call the API, and you'll get the results back. And then you write the code around that, of course. So the documentation is available, and you can, through the API, you can use any programming language. If you use Python, our SDKs are there.
Similar to classical PC like RAM, processor?
No, so this has an FPGA on it. So the big thing that you see is an FPGA. It also has some photonic components. You see? So this FPGA is set up like a Mac. So most of this FPGA is a Mac. We do not use the memory of it for anything other than intermediate storage. It has a high-speed memory interface, but that's just the intermediate storage. So this thing is just doing multiply, add carries, and the photonics provides the nonlinearity, the noise, which does the convergence, divergence of the problem. So this is not a classical compute by any stretch of the imagination. Ising is a well-known concept. If you look it up, these machines do just this one thing. They are able to take a problem with a mixture of variables. So basically think of it like a lot of variables and an interconnection between them. And once you do that, if you let this anneal, if you let it go to the ground state, the variables will go to the state where this Hamiltonian has the lowest energy. So that's the whole idea, that you program a Hamiltonian onto this and let it run for a certain number of cycles. It will tell you what combination of the variables gives you the lowest energy, and that is an optima, a minima as people like to call it. So that's what this machine does. It finds the minima if you give it a Hamiltonian.
Is FPGA same as Spartan vertex like that? Or?
It is a vertex. Yeah, this one is a vertex. It's a fairly high-end vertex because there's a lot of high-speed memory accesses happening here, and a pretty large Mac.
It's available on the cloud. Is it allowed for academic institutions?
Yeah, we allow academic institutions to use it. We like it when they pay for it, but given that they are students, we also give very large discounts or even sometimes free accesses.
Error correction?
So an Ising machine does not require error correction because it's anyways an approximate solution generator, right? So these are problems where you don't need an exact solution. So yeah, so I once
We solve mixed integer problems.
yeah, so a mixed integer linear program is not a direct fit for an Ising machine. You need to do some pre-processing. So that is a very interesting field of work. So if you connect with our team, they will tell you exactly the work that they are doing on it, and how do you take an MILP and convert it into a Cubo kind of a situation, break it down and then solve it.
All problems should have a Cubo form.
They should have a Cubo form. We also support a few other forms where the conversion is done by us. So there is a front end to this machine which converts a lot of stuff into this, and the MILP is also one of the things which they do the conversion, but they are notoriously hard to convert, as you know. If you can develop an MILP solution to this machine, that will be an interesting case study. Right, so
For FPGA programming of VHDL system C is required.
that's correct.
So for this, which programming is required?
For this, no, this is you do a software programming. The FPGA is pre-programmed. It's pre-programmed. The contents are loaded onto the flash. You turn it on, it loads the code. So that is a proprietary code on what goes onto the FPGA. What you are running is just a software interface where, you know, the software interface says take this matrix and load it, and then
Can use it using API.
sorry, yeah, it's an API. It's an
Use it using API.
so you send it a matrix, it sends you a matrix back. Right? So you send it a square matrix, it sends you a 1 by n matrix back, which is the solution, which tells you the state in which every variable needs to be. Right. So this is an interesting machine. I'll tell you an interesting story about this. I once challenged the guys that, you know, can this solve Sudoku? A Sudoku is actually an optimization problem, right? And you know, I don't know if you've ever tried to write a program to solve Sudoku. If you run it on your laptop, it runs in a millisecond. You just say solve and it solves it, and you get the correct solution, right? You run it on this.
NP-hard optimization problems.
It is meant to solve NP-hard optimization problems.
Portfolio optimization.
That is correct. So it can do portfolio optimization, it can do route optimization. So all of those NP-hard problems can be, I never use the word solve with an Ising machine. You can try to solve it. You can get some minima, right?
So is it like simulator using API?
It is not a simulator because in a simulator, what you do is you use a normal computer and you try to, you know, run it multiple times and so on. In this, you don't do that. You convert your problem into a Hamiltonian. So it's an energy function, which is a variable and the linkages between the variables, which is that matrix. The matrix, when you go to the particular m cross n, that is the linkage of those variables, right? And then when you load it, the answer it gives back you is what state of the variables gives the lowest energy. And then you need to write the intelligence around that to decode it, right? So a route optimization problem is a classic QO, traveling salesman, right? Yeah, so that is one of the basic problems which students solve on this. Take a traveling salesman, give it to this guy, give it to D-Wave, give it to Gurobi, give it to your laptop, and so on, right? So in the story of the Sudoku, for example, your laptop does a standard Sudoku very easily, but you can keep increasing the size of the Sudoku. So try solving a 27 cross 27 Sudoku on your laptop. It will not solve. Your laptop will crash, right? Try solving it on this machine. Instead of 1 second, it takes 3 seconds. The problem is it gives you a wrong answer sometimes, because that's what you call the local minima problem, right? So NP-hard problems still cannot be solved, and you probably need a quantum computer to solve some of them, but they can be approximated very well with these specialized machines. So that's what you can use these for. We call it quantum inspired. D-Wave calls it a quantum computer because they use some kind of quantum effect there. But we like to call it quantum inspired. But this is what a lot of the quantum software today solves.
But here we don't need any qubits.
It does not have qubits. We call them variables. This thing can do 10,000 variables. What is the latest version? It's 20,000. Yeah, which is fairly large in size for these kind of problems.
Traveling salesman problem, how many cities it can?
I think in a traveling salesman problem, depending on how much pre-processing you do, I think we've shown up to 70 or 100. Yeah, but some of it due to pre-processing, saying, you know, there are no linkages between these cities. So that's how we make the matrix a little smaller. And these things struggle with sparse matrices. So you try to make them as non-sparse as possible. So yeah, 100 is what.
Why does it have problem with sparse matrix?
It's just how the energy functions solve, right? If you look at the number of minimas in an Hamiltonian, I think as the matrices get sparse, you get like almost a floor of minimas, and it can get stuck in one of those. So otherwise, it's not a problem. I mean, it will give you a solution. You just might not like the solution a lot.
Full stack quantum, how many qubits?
Our first machine is going to have something like 20 to 30. No, there's a version with 4 qubits planned for next year. A 20, 30 qubit, maybe 50 qubit machine in 2029, and that 50 qubit machine will be a scalable architecture. So then you can start connecting them together. These quantum computers are not going to be small. Okay, 50 qubit machine might look like that, which is basically 2 racks. But if you look at what the world is talking about in terms of quantum computers, it's the good old days of the computer, the first computer. Yes, some of us remember those cards. Like you have to be, yeah, you have to be real. I'm not calling you old, but you have to be quite old to remember those. So those occupied a room. So these early quantum computers, people are saying, will occupy a building. And so, but that's okay. I mean, size is an engineering problem. So we are all engineers here. We are happy with solving those problems. The physics is the hard part, and that's where a lot of work happens, right? I'm going to move on to some other stuff that we do. These are parts of a machine of the main quantum computer, but they have other applications. And if any of you are setting up quantum labs, these are going to be like bread and butter experiments, experimental setups, or things you need, right? This is a high-speed homodynamic detector. The specifications we have in this are some of the best in the world. So quantum researchers around the world use it. Even Harvard uses our high-speed homodynamic detectors. This is also a very important part of our machine, which is why we built that. Single photon detectors used across the board. The biggest application of this is QKD. I'm sure QKD must have been discussed here. Quantum key distribution is probably the earliest quantum application that you will see around. India's QKD network uses that box that you see there. Right? We supply it to them as well. And that's a quantum random number generator. I don't have to tell what random number generators are. This one is a provably quantum random number generator. The chip-based ones are not, right? But this one is not a verifiable one. Those cost crores of rupees. We also do a lot of photonic chips, and this is a very new field of chip design, right? And I don't know whether this has come into syllabuses yet or not. The interesting thing is, when you think of chip design, you either think of VLSI, which is basically a lot of coding, or you think of analog, which you have cadence synopsis tools and so on, and PDKs and stuff like that, right? So engineers are doing this day in and day out. This is bread and butter of the electronics engineering IC design community. I have 5 photonic IC designers. Every one of them has a PhD and a postdoc. There are no PDKs, right? So these guys, they understand the physics of how to draw these lines, right? When the way you draw the lines, what happens, and then you use field solvers, basically physics-based simulators to solve it and so on, right? I think, in my opinion, 5, 7, 8 years down the line, all of this will also be PDKs, and we will have photonic chip designs happening everywhere. Why photonic chip designs is driven by the hyperscalers. Everybody wants to route a lot of data around, wants to connect a lot of machines together. You have to use photonics somewhere to do that. So why not run the photonics onto the chips as well? And we are getting better and better at doing this. A lot of material science, material research goes on. We use silicon nitride, 3-5 semiconductors, very, very interesting stuff going on here. And
Also working with
we are not working with ISRO.
We are in touch with them.
Yeah, we speak to them all the time, but they have their, the other thing about some of this stuff is that it is rad hard by default and all that also, right? So people like to send it off to space and stuff like that. That's a packaged photonic IC, so you can actually do photonic packaging, which is fairly complex stuff as well. We do all of this, and one of the things which we started doing recently with the National Quantum Mission is supplying some of these as educational kits to colleges, because how are students going to learn if they don't have the experimental setups? So these experimental setups are available to colleges to buy, and IIT Madras was the first of them to buy this from us. So more of these chips. This is a optical parametric amplifier. Very interesting thing. This theoretically defies physics because it can amplify signal without amplifying noise. So the output actually has a better SNR than the input, which is not something you can do with electronics, but it's something which you can do with light. So You should look this up. Fairly interesting stuff. This is a packaged. We don't look so funny in real life. It's the projector. Interestingly, now we come to our backgrounds, my backgrounds. The three of us have worked together all our lives, but we all come from engineering backgrounds. We are all electronics engineers. We are electronics engineers who took a fancy for physics after doing our first startup and doing an exit to Synopsys. And that's how we started this company. The physicists on the team are Professor Sandeep Goyal from IISER Mohali. He's our theoretical physicist. We do employ a lot of theoreticians, as interesting as that sounds, and they have a lot of very interesting ideas which are very needed because they don't realize what experimentalists can do, so they really push them hard. Anil is an experimentalist. Many of you would have heard of Anil because he's world famous guy, and Aditi is sitting here. I was asked to talk about this, so I was probably asked to only talk about this. Sorry, I spent my time talking about other things. So, hires by educational qualification. I thought you'll find this very interesting. 30% of the people we hire are PhD in physics. A lot of these guys have done their postdocs abroad and so on, and they want to come back to the country. Smart guys, some of them actually design chips. Another 30% is MS in physics. So we basically at this point hire physicists, but this number of engineers is now starting to grow. The reason for that is because we have that Ising machine which can solve problems. That's where engineering comes in. Putting all of these things together needs engineering, and now we've taken the quantum computer to a place where it's moving from the domain of physics into engineering. So that block diagram which you saw, we are starting to build that out. So this fraction is increasing. I think our last 4 hires were engineers, and that's brought the number up to 30%. So we do hire, but what do we look for? We love it if someone comes with quantum knowledge, because starting with the double slit experiment gets complicated. We really like photonics background people. Photonics is fairly different from the way electrons behave, so that's an added thing. Hands-on experimentalists, so in all of your colleges, try to get your labs set up, because if people come for interviews and they've never really seen an experimental setup, it's very hard for them to imagine what we are talking about, right? So, I mean, even our theoreticians, even if you look at Sandeep, he knows exactly what a lab looks like and how things work and so on. And software engineers. This is thankfully quite abundantly available, but where we are lacking is the knowledge of quantum algorithms, optimization, Qiskit. So if these things get added into the curriculum, it just becomes much easier and more direct hire for us. How we work with universities, of course, first and foremost, this is a source of hires for us. We hire from, so far we've hired mostly from IITs and IISERs. We are in an IISER today. We like these guys, but we are looking for engineers also all the time. We do a lot of research projects. I'll show you a slide after this which shows you how many universities we are running research projects with. We also do funded research projects if they are of real interest to us. We participate in educational programs. We do guest lectures, demos, conferences, etc. That gives students a very good flavor of what's happening in the world. And of course, the creation and sale of curated quantum kits, quantum devices. Aditi is the person for that. I've done my sales pitch. And
Sir, are you offering internships?
yeah, we do lots of internships. So at any given point we have as many interns as employees on site. That's because a lot of colleges and institutions now offer long-term internships. So correct. So 6 months works for us. 3 months is a little complicated. There are people who are there for 1 year and 1 year internships and stuff also. We hire a large percentage of these interns. Much of our thing happens through internships and then hires. But 6 months is a good number. I wanted to bring this up showing that we do work with a lot of professors, educational institutions, etc. A list of professors who we work with all the time. We do interact with Umakant Rapol and his team also quite a bit. On the institutions, direct with the institutions, IIT Madras is obviously big for us, and I mean, Anil is on our founding team, so the amount of access we have there is crazy. IISc, this is where the NQM's quantum computing hub is, so obviously we know everyone there. We also do some funded projects there. Tampere University in Finland is a very interesting place for us. They fabricate some of our 3-5 chips, and you know, a lot of that 3-5 chip based research, quantum dots, all of that happens there. In the US, we work with the University of Maryland, and the ICER that we work with right now is ICER Mohali. That's more on the theory side. A lot of government industry partnerships and stuff like that as well. Okay, sorry, I'm running a little late, I think, but that's because we started late and had compute issues. I'm going to leave the presentation on and questions.
Obviously, we would like to send our students as interns.
Yeah.
I'm from Sunil Bhatt from NIT Nagpur.
Okay. We work with a lot of NITs, don't we? But Nagpur, I don't think we've ever worked with. Yeah, we are very happy to do that. Our process of selection involves an interview. Our guys are very finicky about who they bring on board, but once they bring on board, we actually pay better internship than Google is what we have been told, but we make them work as well, so they learn a lot. So happy to do that.
Into the second year of quantum minor.
Now
these guys will be in third year now.
Third year is good. Second is a little early for us.
They will go into third year now.
Yeah. So third year works nicely.
That will be the most suitable.
That's correct. Third and fourth year students are better than first and second year students for us. Definitely. James, can you pass on the information to them? Maybe you have a group with them or something. So that machine has some fairly high-end systems. It ends up costing around 40 lakhs. Yeah, that's. Yeah, it does need a standalone machine along with it. It needs like a server with it, or you can also connect it to AWS or something like that. So that is what it requires, and
Independent machine, or
it's an independent machine. It comes with a Ethernet port, so you plug it in and the machine is up and running. But if you want the software stack which converts other things into QUBO, if you're directly giving a matrix, this machine is good enough. If you want something which does more processing, converts it into the matrix and all, that requires a standard computer. So it requires either a AWS or a server to do that.
You said Python is the requirement, right?
Python, yeah. You can write a Python program and call the API. If you call the API directly if you call the API where you pass the matrix directly, then only the machine is needed.
So whole problem statement we need to convert into a matrix and then can be passed.
That's one way. The other thing is we provide some standard accesses where some standard kind of formats it accepts. So if it's an optimization problem in a certain format, maybe an MILP or something, you pass that on. There'll be a software layer which will convert it, break it down, do the matrix, take the answers back and give you the answer back. So those higher level APIs require you to have an AWS or a server along with this machine.
In the higher level language.
That's correct. So they can write their own programs, which is why we allow access to direct matrices as well. So there, no, you can do it.
Python is not supporting fully, right?
You can do it with whatever you want. It's an API, so it doesn't matter. It's a standard REST API. You can do whatever you want with it. Any language is okay. It doesn't care what language it is.
Ultimate output and ultimate input to machine is the matrix.
Matrix, that's correct. So we also work with a lot of the national and state quantum missions. So there are quantum missions in Andhra, there are quantum missions in Karnataka. We have Maharashtra is interesting. We've been trying to work with the quantum mission in Maharashtra, and they said that training and development is what we are going to focus on, which is good. It gives us more talent, but these Andhra and Karnataka guys are putting in a lot of money, right? National Quantum Mission puts in direct money into companies and so on. So we work with all these people, of course.
What are the use cases already addressed and solved?
I'm going to let Aditi take that because this is what she does all the time. Aditi, maybe you want to.
So we have solved use cases in multiple domains. So for example, anomaly detection, it covers a large umbrella of use cases. You can detect anomalous data in transaction data sets. So for one of the big 4 companies, we did risk analysis. We helped them to do risk analysis using financial detection. So we also showed that our machine was 4 times faster than the machine learning algorithms that they were using, standard algorithms. So that is one use case. Another use case is we work for a very large company, Aditya Birla Group, and their textile arm, we helped them to optimize the purchasing price of their raw materials. So there were a lot of different constraints involved. The quality of raw materials, the price point, making sure that shipping containers are filled to their full capacity. So multiple different constraints, and all had to be done within a small amount of time. So yeah. So we helped them to optimize the purchase price of their raw materials. We showed a 4x improvement in the savings through our solution.
Have we explored these use cases somewhere so that we can understand the workflow?
Sure. So what I can do is we have a few case studies that we have
detail explore. We wanted to understand the workflow so that we can decode exactly what to be done at the pre-processing level, what to be done at the compute level, right? That we can understand. Many of the PhD students have started working on such a problems, right?
Okay.
They are preparing the quantum platform to work on.
Okay.
But not exactly understood how the workflow should be.
Okay.
What to be pre-processed, what to be compute based.
Okay.
So in order to understand if some use cases are given with the detailed workflow, then people can refer it, can understand it, and split the problem and can solve it.
Yeah, sure. So like we mentioned, this is sort of the kind of model that we are working with IIT Indore. So they purchased this Ising machine from us, right? And we are helping them formulate exactly these kind of detailed use cases where students can understand exactly end-to-end in-depth workflow of the use case, exactly the kind of thing you're saying. So yeah, we are happy to engage in that way and help out students understand.
I think the CVRP has a detailed workflow.
The CVRP has a detailed.
Can open source it and publish it.
Yeah.
So CVRP is the capacited vehicle routing problem. So n vehicles with some capacity need to deliver goods from central locations to multiple locations, right? This is a classic NP-hard problem. So that is like the example that we use for running on this machine. So we can just give you the source code for that, and you can see how things are done.
Is it possible to arrange the demonstration?
We can do that. Yeah, we can do
We
that.
can do that.
We can arrange for a demo.
Here you are seeing. In this code.
I will get somebody from Bangalore to do it for you because they will.
You try to simulate one case.
Yeah, they do that all the time. So if you go to any conferences, you will see our guys there showing these live demos and.
There are 5 institutions VNIT,
Okay.
DJTI Mumbai,
Mm-hmm.
COEF Pune,
Mm.
and back to Lonere, right?
Okay. So
If
just
we demonstrate here, we'll all get exposure. Maybe
We
we
can-
can plan.
Yeah. we can do that. I mean, I'm sure that is
We
a
are here till 70.
yeah. Maybe Aditi, if you can take
Yeah,
that action.
I will, yeah, we will
Uh,
arrange something,
Just
absolutely.
some trivia. COEP. So we are proud COEP alumni. So both me and Ravi are from COEP. Okay. Cool. Any other questions, or we'll close for the day?
Thing else, right?
We'll do details.
Yeah, we will.
We have put it on the group. Yeah. So two things we have given: the sales contact what we have shared for people who want to require kits for the quantum lab, and we have given the email for the internship process. Okay. Please contact us.
You can give them my details as well. You have my details.
Okay, I'll give.
My mobile number is 7259 88 6944. 7259 88 6944. Sujoy Chakravarti. Yeah.
Know how to reach us.
Okay. Thank you so much. Thank you for.
That's the last thing.
Oh, okay.
Thanks for your
Thanks.
time here.
Prefer. Thank you.
We'll be calling you. We'll be calling you.
मी मराठी माणूस आहे.
We'll be calling you more frequently.
Okay. 100% महाराष्ट्रीयन.
Yes.
फक्त नाव महाराष्ट्रीयन नाहीये.
Ma'am too. Yeah. चलो.
Exactly. Huh? The card, yeah, I'll give you the card.
FTP group.
Okay, sure. Thank you. Yeah.